Okay, ladies and gentlemen, then here we are again. Go back to the point where we were. So we will send you this, correct this here. Now it's in the correct spot here, almost. You can see here, this is not correct at all. The one here, this needs to be RD, so it's very easy to follow up this, and then you get the standard values. You get the MLSS of 3.78. If you take the sludge volume index of 100, 2 hours thickening time, factor for the scraper of 0.7, and return sludge ratio of 0.75. Then you just fit this in this formula, and this is what you get. Anywhere else you get it for meters. Okay, everything else, and up here also is somewhere the formula. Let me find it out just a second here. In the text, formula how to calculate it. Upwards here. Sludge volume circulating, and by dividing this we might give it fat. Can't do it here. I'll do it in this computer. But this is also important formula. We need to calculate QA, and that will be in the range of so this was the correction for what we did yesterday. No, there's a plus here. That's correct. Okay, and I think we have to restart this. You restart here, right? Because this scheme is something that's really a very basic relevance. There's nothing more important than Monod, and there's nothing more important that you understand how to operate continuous fermentation and the growth on a discontinuous fermentation if you want to become a biotechnologist or want to deal ever with microbiologic processes. This is the very two basic things. And then you've got to have, again, what any process engineers needs to know. You've got to have from the chemistry, your stoichiometry, and from process engineering, you've got to have your balance. Mass balance, component balance, energy balance. This is the basics of any biotechnology. Well, in biotechnology, if you want to invent it, you have an understanding of microbiology, chemical pathways to deal with that, but the basics of operation, the processes, is continuous processes, Monod. So the growth rate is dependent on the FM ratio, on the food mass ratio, and if you have a large food mass ratio, you approach the maximum growth rates. There can be other inhibiting effects you have to be conscious of, but mostly it's not. It's just like this benzene mode, you get benzene, the gas gets charged, and normally it does run. There's a few things that might go wrong, but normally 80% is active. And this is also the problem in bacterial growth. You have to have a microorganism, you have to have substrate, and under aerobic conditions you have no air, In the anaerobic conditions, you have to have the right temperature. If these three things fit, then you might check the pH, and you're through with which standard. Then everything else becomes more complicated, and you've got to have a hint where to look for if you look for inhibition by any toxic influences. But that's normally not okay. You don't put any toxics in your reactors. You know that what you're doing. So 90% it's temperature, oxygen, no sludge, as you know, no microorganisms fed, or no food. No? So that's the standard problems. Now, if it becomes slightly more complicated if you have to deal with more than one microorganism you want to stabilize in your reactor. That's what we have to do in our activated sludge tank. We have to stabilize the heterotrophs, and we have to stabilize the nitrifiers. And what else we have to do, we even have to separate our tank into compartments, because we have to have one compartment for the denitrification, because we don't want there dissolved oxygen. And we have to put there, we have to supply we have to have there, of course, our nitrate, and we have to have there our microorganisms. So to start with, let's just kind of put this in here. So we have nitrification. What do we need? We need dissolved oxygen, major or equal to 2 milligrams per liter. What do we need? We need nitrifiers. And we need ammonia. For denitrification, red here. So we don't want, there's so many reds, I hope one will work. Okay. A DO of less than 0.2 milligrams per liter. So these two things do not match. Then we need nitrate. If we don't have nitrate, we can't denitrify anything. And we need heterotrophic bacteria. Okay. Now for COD elimination. That's elimination. We need DO larger than 5 milligrams per liter. We need COD BOD substrate, and we need heterotrophic bacteria. So if you look at these three things we have here, this is the three tasks which we have. 1, 2, 3. Since in the wastewater inflow, We have COD, BOD. Oh, I forgot something. And we have ammonia. And we do not have no nitrate, no? Okay, very important. For denitrification, I forgot something. What we need, and that makes it complicated. We need COD, BOD. And because the same heterotrophic bacteria that degrade COD, BOD with dissolved oxygen in the COD elimination, they do basically the same process in the denitrification, only they have nitrate as an oxygen source. So they have a little bit harder job in the denitrification than they do have in the COD elimination. And for that is that they only take the oxygen from the nitrate if they do have, if there's no dissolved oxygen available. So if we look at this, we have our inflow here. And then we can go to 1 and 2 because everything we have BOD, COD, we have ammonia. We can we just have to go heterotrophic bacteria and nitrifiers. This is our task, but then we can do that together. No, we can do 1 and 2. And establish it's always German, CH. Establish heterotrophs and nitrifiers. Right? But then we have a problem. Then the effluent will be nitrate, but it will be no COD. And of course, in the effluent will be heterotrophs and nitrifiers. No? So denitrification, if we want to make 3, we need to add COD here. No? Where we get it from? And if we add it, how do we control that we don't add too much? Because we don't want to have it in the effluent. It's the effluent should have, ideally, no COD, no nitrate, no ammonia. No? So what we are talking yesterday about is that you can, how do you do this job here? How do you establish heterotrophs and nitrifiers in an aeration tank? Well, you just have to control the FM ratio to be as low that the nitrifiers are going to have safely a higher growth rate than your heterotrophs. The nitrifiers are so nice that they have a very low Ks value. That means that even when you reduce FM ratio, because FM ratios for the nitrifiers and for the heterotrophs are of course coupled, because this is, you have a certain ratio here. You have 120 grams COD per population equivalent a day, and that makes like 60 grams of BOD, this is standard values, per PE a day. And that is all humans produce that. And PE is population equivalent, and if you have industry, you just measure how much, what is the concentration, and then you just convert that to the load when you multiply the concentration with the flow, and then you get a load, and the load you divide by this factor, and then you get the PE. This is how we calculate that in Germany. Internationally, it's more popular just to give the flow for a wastewater treatment plant. Comes in the US, they always talk about a treatment plant having so and so much MGD, which means mega gallons per day. Nobody else in the world knows what a gallon is, but I think it's not as good as in European version is the PE, the population equivalent, because a wastewater treatment plant you have to design according to two criteria. You have the hydraulic load and you have the organic load. Yes, it's true, 90% of the construction is basically determined by the hydraulic load. We talked about that. Now, all the mechanical units, what we've talked about, screen, grid chamber, primary sedimentation with its residence time, average residence, all is, and all the channels and all this kind of stuff is determined by the flow. So this is for the American way. Only the aeration tank and everything that in the sludge treatment, that's determined by PE. So what do you really know? You really need both. You need the flow and you need the load. Because for any design, you have to make a hydraulic design and you have to make an organic design. The biological treatment of mechanical treatment is mostly determined by the flow, by the hydraulic load, and the biology is mostly determined by the organic load. So now we are in treating the biological treatment stage. So phase stage, yeah. So we have to talk about the organic load. So we talk about the PE. And the ammonia here, well, this is normally reduced by, this is ZK, influence influent of the treatment plant. And this is after primary sedimentation. It's primary sedimentation lowers it to 80 and to 40 more or less. And ammonia is about 11 grams per nitrogen per PE day. That is ZK, and it's lower to 10 micrograms. Because, well, it's not really ammonia, it's total nitrogen then. That's lower to 10 grams N per PE a day. We always look at it ammonia because whatever enters in form, even in form of organic nitrogen mostly, is deammonified, as is hydrolyzed to amino acids. Amino acids are deammonified, so it all goes through ammonia at the end of the day. Okay, this is the load what we get in here. We looked at that yesterday and looking at what happens in the COD elimination. We had that when those 80 grams, 40 grams of COD are mineralized with 40 grams of oxygen, and they produce water and carbon dioxide, and 40 grams of COD are assimilated and restructured so they make up the cell growth and the anabolism, and also part of the ammonia, but only a small part of the ammonia goes into the cells, and unfortunately the cells in the sludge treatment are 50% again degraded, and the ammonia is going to come back with a filtrate from the sludge treatment. So so we just have a very low ammonia elimination in the COD elimination, and most because due to the sludge treatment later, and then at the end of the day we have to get rid of most of it by nitrification, denitrification. Okay, in order to get the nitrification done, we have two types of nitrifiers. We have the AODs, ammonia oxidized bacteria. We looked at that yesterday. They still have nice gain of reaction enthalpy, which is almost comparable to what we have in the aerobic respiration here with 112 for carbon, and in the first step of nitrification, which is the nitridation, where the ammonia is oxidized to nitrite. We have 78 again of Gibbs free energy, or whatever you call it. This is a little bit an odd unit. This is kilocalories, an old unit per gram atom. Kilocalories, it was easy to memorize because a kilocalorie is the energy you need to heat up 1 kilogram of water by 1 Kelvin. That's it, no? And anybody should know the specific heat for water, which is 4.19 kilojoule per kilogram in Kelvin. So the conversion factor from kilocalories to kilojoule is just multiply the kilocalories by 4.19 and you have it in kilojoule. So it's not really that difficult. I think it's easier than the horsepower to kilowatts because I don't have to do that much, no? And it's an odd factor you can't really explain. No? The second step, this is the nitritation. The second step is the nitratation, and this is where the nitrite is oxidized to nitrate. And there you see this is only 1/3 or less than 1/3, almost only 1/4 of the enthalpy. You don't need to recall those numbers, it's just a relation of them. So the unit is not that important here. And then you see again in the denitrification, where nitrate is used, the oxygen from nitrate is used to oxidize again COD, which is the same COD you have up here. And therefore per C you get just about 75%. It's a little bit more than 75% of the reaction enthalpy and the denitrification. Because if you don't memorize anything from this course, you should memorize that bacteria are longer on the earth than human beings. And if you give bacteria the chance to make energy and so they can grow, they would do a good job. No, if you don't torture them with any environmental conditioning like too much, too hot, too cold, like too much pressure, not enough pressure, or whatever, and you have to supply them food and oxygen, at least the aerobic bacteria, and then they will do their job. Humans not always do their job as good even when they have good conditions. So humans still have to learn that a little bit. No? But okay, we still have some billion years to learn that. To be as good as the bacteria, great as good as a thermodynamical energy enthalpy gain is. If there's great, they do a great job. If it's small, you have to be nice to them. No? And they won't grow as fast, and then you have to take care you don't lose them. Okay. So now we know if you push too hard, if you feed too much water to the bacteria, because FM ratio really means the mass. We have learned by looking at the secondary clarifier, we can just concentrate the material mass in our activated bloodstream to a certain degree. We have seen the formulas yesterday. I had a smart work here. We have set standard. We have an SCI 100 milliliters per gram. We have normally we provide 2 hours. We have to respect that in 9 hours of treatment. time in the secondary clarifier, we have scrape effector, normal scrape, split scrape, scrape effector. That is scraping plus Now we know that the solid concentration of it yesterday at the bottom of the secondary clarifier is 100 or 1000 over SDI times square root of time here. We got quickly in the next one here. No, I can't. I have it here, but I can't do anything.
That's weird.
So never mind. We won't screw around with that. But I can't do anything in that in the Word document either. And I didn't understand that yesterday. So I have to use my computer for that. It's 10 times 2, oops, to the 1/3. So that's 12.6. Then I have to multiply that by 0.7. That makes it 8.8. This is the same value. So this is my CTS in my return sludge is 12.6 times 0.7 is 8.8. Is that right? And now, and I did not do that yesterday, right? My CTS BB is equal to RV over 1 plus RV times CTS RS. And this is what we had to do that we had Q ZB plus QRS times CTS VB is equal to QRS plus QSS times, CTS RS plus QAN times CTS AN. And if you recall, we had this final clarifier here. And this was from the aeration tank here. And here we have CTS BB. And here we have our QRS. And we have CTS RS. And we mix that together here with our QZB. And so So what comes out here at this point, we have QZB plus QRS. And of course, since this is a completely mixed tank, we have CTSBB coming out. This is our component balance. This is our inflow load of TS into the final clarifier. And here we have QAN, which is equal to QZB, almost. And we have CTS-AN, but this is close to 0. Because we don't want to have any flux in our, or biomass in our effluent. This is why we have the final clarifier. We have clear water here, and we have the sludge down here. No? Water is supernatant, no? And we have here our Q surplus sludge, and that has, of course, also CTS-RS, because it is the same stream here. And at this point, we would have CTS-BS if we would operate the scraper, right? Just so you find all the things. And so what happens is, this is close to 0. Okay, now this one is nice. And this is, whoops. Oops. No. Oh. Now I mix caps here. Okay. Well, it doesn't really matter. It's a green stick anyways. So this one is equal to QRS because QSS is much smaller than QRS. So at the end of the day, from this formula here, this results to be, if we say this is CTS-BB, is equal to QRS divided by QZB plus QRS. Just bring this factor here over to this side, times CTS RS. So anything, what we do is now, we divide everything here by QZB. And then we define RV is equal to QRS divided by QZB. And then you see from this formula results, this is RV here. This is 1, and this is again RV, and then you end up with this formula here. Right? Okay, and if we hand this in and say RV is 75, then you end up at 3.78, I think, is it? Here's 3.78. Okay, now and this is what we have in our systems here. This is here in our balance. This is why we normally say this is anywhere close to 4 grams TSS per liter. No? because it's pretty close. And this is what we normally operate our aeration tank with, because that's what with standard values our biology system will give us. Okay. So this was, I repeated this from yesterday. I think I can touch out these. Not yet. Okay. Now we give you time to copy it. But you will find it also in the TSBB is MLSS. I said that yesterday. No? And the most American literature, this is also MLSS. This is equal to that one. Huh? So when you take the Metcalfe and Eddy, the standard work for wastewater treatment from the US, which is in English, then you will find MLSS. No? Okay. Please tell me. Okay. As a judge out yesterday, I had a mistake. I had a 1 here. This was just wrong. Please take the one which is from today here. Okay, then I like still to explain, because I think it's worth taking this time for it. How do you have to read this one here? So these are the heterotrophs. And these are the nitrophiles, or autotrophs. Okay, now we start with the heterotrophs. We start with what I told you, each of them is 10. We put our food in here. And now we look at mu heterotrophs, no, is major to mu autotrophs of mu nitrifiers. So that means we have T is glass 0 plus the doubling time of the heterotrophs and the doubling time to double is 1 over mu heterotrophs. Because the growth rate is defined in how many bacteria grow per unit of time. So if you have one bacteria growing per unit of time from one bacteria, you got the doubling time. And this means, for example, and we'll say that mu, to make it radical, we say that is equal to 0.5 times the growth rate of the heterotrophs. So what's going to happen then at T1? We're going to have 10. And those guys have doubled. And these guys, they're the 10 that were there, but only 5 grew, no? So, but now, since we just can take, we just can have in here 20 bacteria, because this is our, all this 20 microorganisms, 20 bacteria, is equal to our 3.78 grams TSS per liter. This is what we can stabilize in our aeration tank. Because from our aeration tank, all the bacteria will flow into the secondary clarifier and they will come back. They will thicken. And we have to take out, whatever grows, we have to take out a surplus sludge. So now we have to see that we have to take 20 bacteria. So all bacteria have the same chance to stay in the system or to get into the surplus sludge. So now we have here 30, 10, 20, 30, 35 bacteria. So 15 bacteria have to go out. So we have 1, 2, 3, 4, 5, 6, 7 in a row. Yeah, so it's really what happens is those 7 go out. This is 14, and then half of each one, like. This is surplus sludge. And this is again 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And those 2 halves is 20 bacteria. This is our aeration tank. Or return sludge, no? However they will come back to the system. So our new start conditions are after we take our return sludge, 1, 2, 3, and again. Like this is just half of one there. This is this column and this column. Here we have this is this one here, no? This is 1, 2, 3, 4, 5, 6, 7, 8 and a half. 1, 2, 3, 4, 5, 6, 7, 8 and a half. Okay, and now you see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11.5. No? So we start out with 10 and 10. And after one doubling time, the result is, and taking out the surplus sludge, the result is that we have 11.5 and 8.5. So now you can continue that, and you'll find out it just takes a few times, and you just get less and less nitrifiers, and finally you won't have any nitrifiers left. No? The heterotrophs will overgrow the nitrifiers. Since they have the most food, no, there's no reason. It takes for the nitrifier. It takes a lot before once you're here before they get into this range. They will never get there. Because you know the growth rate is not going to be reduced. If MA ratio is reduced, it takes a long time before you're below the growth rates of the nitrifiers. With the nitrifiers, it's different. The nitrifiers will grow once you're in this. You're anyways in a low region, and the nitrifiers then will grow with the maximum rate. But then when they get more, and they will reduce their growth rates to the growth rates of the heterotrophs. They will not take the heterotrophs completely out of the system, and that has to do because the heterotrophs have much more food than the nitrifiers. It will not work out vice versa. It will not work quantitatively, because it's not 10 to 10. It's maybe 100 to 5. What the start ratio is. Huh? The nitrifiers are pushed out of the system rather readily, when whereas the heterotrophs you can't push out of the system. Okay. So the consequence is, in order to establish a continuous fermentation in a bioreactor, solid retention time needs to be equal or longer than the time the microorganisms need to double for bacterial growth. As the growth rate is the inverse of the doubling time, the criteria for stable continuous fermentation is that SRT has to measure to 1 over mu. And SRT, what is SRT? Yeah. But how does solid retention time relate now to our system?
So basically what you're measuring is just basically measuring how much of the surplus sludge that you're moving, right?
Again?
So you just, with the solid retention time, you just basically want to make sure you're not moving. You're basically controlling the rate at which you let the surplus sludge spill over, such that you're maintaining.
Exactly.
Yeah.
And what's the equation for that?
That I don't have on the top of my head.
Okay. But this is what engineering is all about, no? You create a model about something, then you find an equation, then you calculate, and then the result of your calculation you interpret back to the model, and then you know what you have to do. You know how HRT, hydraulic retention time, how is that defined?
I mean, that's just how much of the liquid you're holding on to per unit of time.
Again? That was too fast for me.
Sorry. It's basically how much of the liquid phase you're holding on to per unit of time.
That's only partly right because you make it too complicated. Explain it to a guy who's 3 years.
It's
So make a model. You know, engineers always like to paint. I have a tank here. How big do you want to make the tank?
make it 1 liter. 1 liter.
1 liter. Okay. Now, how do you have a flow in here? How do you define the HRT?
So wouldn't that be the ratio of the inflow to the outflow over the volume of the tank?
Too complicated? No, what?
Complicated?
It's again always helps to make one of the biggest tool and for the engineer is what is the unit of HRT? What's the dimension of it? Is meters, seconds, kilograms per second and square meter, or what is it?
I mean, it would be a unit of volume per unit of time.
Cubic meter per hour for HRT for a time?
No, not a cubic meter, but what are you getting at?
Well, you're too scientific. The unit of a time is a time, seconds, days,
Yeah,
whatsoever.
Yeah.
No? And as engineers, we always see big. We talk in days. And if you have 1 liter, now if you want to have a residence time for 1 liter in 1 day, what's going to be your inflow?
Pretty low.
Yeah, what is pretty low?
I mean,
1 liter, amen.
1 liter? Flow has what unit? Flow. The flow is? What is the dimension of a flow?
liters per hour.
Liters per hour, a liter per day.
Liter per day, yeah.
So how many liters per day do you need?
1 liter in per day.
Right.
1 liter out per day.
So what is now the function of it? It's not that difficult. It's volume, the volume divided by flow. No? This is in, I write cubic meters better because really it should be second here if I'm consequent because what is the system? As meters, kilogram meters in seconds. That's the IC, the international system. No? And in but in wastewater we talk always cubic meters per day. So the unit is day, and that and then we flow. So now the SRT. How do you think? What is going to be the unit? We want SRT in here.
Kilograms or?
No, it's a time. Solid retention.
Of course, yeah. So
It's days, no? Okay, and how is it going to be if you look at here?
amount of solid in, amount of solid out, so it's
No.
the solid over the flow of the solid.
Okay, more or less, it's mass in the system over mass flow. No? And this is kilogram. The mass we look at is kilogram TSS, and it's kilogram TSS per day. And this is obviously equal the volume of our aeration tank, no? Times CTS BB, no? Or let's put it right, MLSS, no? So we have the volume of MLSS, and that's over the flow of the surplus sludge times the concentration TSS of our return sludge. Now, and this is again equal 1 over rate of the nitrifiers, because these are determining our solid retention time.
What is the rate of variation?
Hmm?
A volume aeration.
Volume of the aeration tank. No? This is our volume aeration tank. This is our, here we have our CTS BB, which is equal to MLSS. No, SS is big. Minusculous, capital letters. Here we have our QSS. And we have here our CTSRS, no? And this measure in lab. This is what the microbiologists do for us. And then we put a few safety factors on, because biology is always nice. And in the rough environment in a sewage treatment plant, we're not so nice. So we're going to have some inhibition. We don't have such well-controlled things. So what normally we want is we had for this one. Because if we have to design a variation plant, this is our question mark. This is what we as engineers want to figure out, right? We want to figure out how big do we have to do this tank. Because we have already figured out, we discussed that lately, we know the depth and the diameter of this tank, so done. And if the diameter is too big, what do we do as an engineer? If the result is 60 meters of diameter, so construction becomes pretty difficult. Well, what do? We make 3 tanks, 2 or 3 tanks, no? So, but we know the surface. If we know the surface area, we're going to figure it out, because the rest is just engineering, finding what you can make technically. That has nothing to do with sizing. Then it's then this is where we go from the dimensioning, from the process engineering to the real constructive engineering. No, this is not possible to do this in a course. There's different courses where you learn this. What's reasonable and what's not reasonable. So, anyways, if you have a bigger plant, you want to have like on a small plant, if the result is 20 meters in diameter, that's good enough. You're just going to make 1 tank, no? But what do you do when you have to repair something there? Slightly a problem. So you have to see that all the mechanical installation you can just remove, and that the tank will more or less work even without this mechanic installation, because if that breaks down, you have to survive a few days until it's repaired. Well, if you have a big plant, you're just going to have multiple, and you're just going to have 1 tank in reserve. So you just can take out 1 tank of the system, repair it, and just sleep easy. No? But this is plant and engineering basis. This is a different base. Has nothing to do with microbiology or the reactor design we talk about here. In this reactor design, so we have defined this tank. Now we are in this business to define this tank. This is what microbiologists tell us. So you know what this QSS times CTSRS is? This is something you're very much used to. You always look at it as a microbiologist. This is what the problem of communication often is. This is your yield factor.
Yeah, okay, that makes sense. Yeah.
What else is it? No?
Yeah.
So this is what microbiologists, this is why, everybody speaks a different language, no? This is the problem we have, no? This was when I was talking about how do the microbiologists call respiration, the chemists call oxidation. Well, if you don't know how to communicate, you might consider different things. No, this and this is nothing but your yield. No, this is your bacterial growth. This is because you know how much the food is. Out of the food that we supply, we know this is a 50% of our COD, and if we know our COD ratio to the OTR, also to the VSS, also volatile suspended solids, and if we know our ignition loss of our bacteria, we can predict how much is our growth, and then we have everything. This is our in our standard. This is our 3.78 grams per liter, not TSS. Now we just need, we're going to have our food. Our food is our BD COD, which is our QZB times C COD. Now this is the load of COD, this is the flow, and this is the concentration of COD. And then our QSS times CTSS RS is equal to our BD surplus sludge, no? And this is our yield factor times our BD COD, no? In this yield factor, we in wastewater call the specific surplus sludge production, USD, no? In kilograms of TS per kilograms of COD. And if we have that, we can calculate the volume of our ration tank. And then we can design our second tank. Überschussland, ne? US, ne? Also wo die SS, yeah, surplus sludge, no? Surplus sludge production. But since all my graphics and all this kind of stuff is in German, if you want to relate the graphics with what I tell, I have to use those strange signs, no? In English, surplus sludge, well, you know, specific surplus sludge production. Specific surplus sludge production. Also ESD ist, oops. So there's two things we still have to. We have, in order to be fit, we have this here. This is a little bit our problem, and this is our problem. This is what we want to know. This here. This is still what we have to talk about. This I explained, this we want to calculate, and these two things we need to know, because then from this we find our SRT, because we just got inverted, and this is what we want, no? This is how we dig through the sizing of an equipment. So I think I can take this away here. Not have too much on the whiteboard. And now I'm with you, Sean. No? I also love my blackboard, and if I have two and I can exchange them, I'm going to use them.
Yeah. Professor P, just out of curiosity,
Hmm?
so if, so like a lot of the heterotrophs that my students deal with have doubling times somewhere between 20 minutes and 3 to 4 hours. These nitrifiers, they grow much more slowly, like how much more slowly?
As a, we'll end up. This is a little bit before. We approach this a little bit different. We have so-called treatment objectives. And the one is only COD elimination. And there we have as SRT in days and sludge loading, BTS COD. And this is kilograms of COD per kilogram of MLSS and day, not as a unit here. And in COD elimination, let me just try to make this nice again, because this is treatment junk. Let me see how I get this done here. Treatment objective. And then we'll make this here SRT and BTS. And this is in days. And this is in kilogram COD per kilogram MLSS and day. So then we'll write this a little bit lower here and make a nice table out of this. Yeah, this is high. And this is COD elimination. And this is 4 to 5. And this is 0.6. Then we have nitrification. This is 10, also 8 to 10. And then we have, this is 8 to 10, so this is about half of it. This is 0.3. And then we have nitrification, denitrification. It's about 15 something. So it's 0.15. And then we have simultaneous sludge stabilization, which is also called extended aeration. No? Only extended aeration doesn't explain it. No? And this means that you just, in extended aeration, you aerate the sludge that much that it's stabilized. So it will not, when you separate it and store it in a tank, it will not start really to digest rather readily. Finally, it will, but it's it can work with that, and that's normally 25, and that's 0.05. No? And this is all for T is equal 12 degrees centigrade. Because if you're at higher temperatures, you can reduce that. No? Because you have then then your mu max goes up, your required SRT goes down. That's temperature dependent, no? I think every 5 degrees it doubles or something like that. It's a Arrhenius equation, no? Okay? Answers your question so far.
Yeah.
Okay, now I found the right tops to the pens again.
Yeah, that's always in trouble.
If SRT is less than the doubling time, more organisms are washed out of the reactor than grow in that time, and the microorganisms shall depleted in the course of time. If SRT is longer than doubling time, more microorganisms shall grow than are washed out, until due to a lower FM ratio, due to an increased microorganism mass, growth rate of the microorganism is so very reduced that doubling time shall be equal to SRT and stable conditions are established. No? And this is also with this here. What happens is it really doesn't help you much if when the heterotrophic bacteria get less, because this doesn't really help you too much with your nitrifiers. They can't go faster because they already grow as fast as they can. So they can't really, even if heterotrophic bacteria, due to the FM ratio, decrease, that doesn't help the nitrifiers, because it is the absolute numbers of heterotrophic bacteria grown in a certain amount of time, when you're in this area here, is always the same. Even if there's more bacteria and they have a less grow rate, then the yield of the bacteria stays the same.
Yeah.
And this is why when you're here, you're lost. No? The nitrifiers will be expelled. There's no way you get there because the FM ratio is too high. And even if you get more heterotrophs and their growth rate goes down, the absolute number of heterotrophic bacteria growing in this time is always the same, because the yield is constant.
Right.
And since the yield is constant, no, once you're in this range, they just grow faster. There will be more. There will be a constant number of heterotrophs that grow. This is also the same thing here with the nitrifiers. They will always grow the same numbers of nitrifiers here, but the SRT will the growth rate will be at the end of the day the same as for the heterotrophs. But once you're here, you're lost. Because you got to look at both things when you make this diagram, which I made. No? Is you can grow the number of because you supply a certain amount of food, and from this food, and the yield is constant. Well, almost constant. It goes a little bit down when you have a lower FM with reducing FM ratio. The yield is a little bit less, but this is not very much. This doesn't change very much. And due to that, the absolute number of nitrifiers or of heterotrophs growing in a period of time is always the same. And this is only influence if you're here, then more heterofiers grow than nitrifiers. If you're here, nitrifiers are growing that much so that they can eat their food entirely, and that's a stable condition. Here, nitrifiers will not be able to eat their food entirely, but heterotrophs, because they can grow faster, they're going to eat their food completely, and they're going to produce always at this rate. And if you get here, nitrifiers just don't have the time to eat all the food, and due to that, the replication of them will be less than the heterotrophic in relation. So you got to see at both things, at the growth rate and at the yield. And then then you get to this interpretation: stable, unstable, no notification, unstable notification, stable notification. No? Okay, so it's obvious that for a stable fermentation, the number of microorganisms you take out of the system has to grow in the time. You can't take more. If you take more bacteria out of the system than grow, it's going to be less and less bacteria, and finally not going to have any. This is unstable, and if you have a growth rate of the bacteria, the yield will limit the maximum growth rate. So the food will be eaten, and there's no more food. So you can't grow. There can't grow more bacteria than the food that's there. And if they become more bacteria because you take less out than grow at a certain moment, then finally, because they grow more, the ratio of growing will, because there's more bacteria, but the ratio of the bacteria of the growth will reduce. But since it's more bacteria, it will be always the same number of bacteria that grow. And finally, there won't be growing more than you take out. No? They'll all eat the food, but they grow at a less rate. No? This is what stabilizes the. So whenever you're below your salt retention time is higher than the inverse of the growth rate, you're fine. And whenever it's reverse, you're lost. There's just those two cases, no?
Just out of curiosity, when your solid retention time is too high, you're sort of drifting towards unstable, just to completely wash out your nitrifiers. What steps would a plant operator take other than to increase the SRT or increase the SRT? I mean,
he has no other chance. He can do. If he has a problem, like if the plant is under-designed, he can do what he wants. He's not going to get it stable. So the only thing he can try to raise his MLSS, and that's what operators like to do. No? They like to increase the MLSS because then they have reserve. So nitrification is going to be stable. But whenever it comes stormwater, they have a problem because they then this problem comes up here. This is where you have the problem with the secondary clarifier. Then your storage zone is too small, and your storage zone is going to go up, and your sludge is going to flow away. Then you have a problem that you have during stormwater. Finally, you're going to get sludge coming out of your secondary clarifier. And if that, and notice anybody, they're going to make you stress because this, of course, is again oxygen depletion in the receiving river. So we always talk to the people. Your plant is properly designed, so why don't you operate it properly? If it's designed for 4 kilograms MLSS per liter in the aeration tank, why don't you operate it? Why do you go up to 6? You can go up to 6 as long as you don't have maximum flow. Because if you have if you have less flow, then of course you can all these zones you can expend more because your sludge volume you load onto the secondary clarifier is lower. It's not maximum. But what happens if rain comes? And that comes suddenly, and you're not going to get your sludge out of your system that quick because also, because you have a pre-thickener, mechanical pre-thickener here with a limited capacity and all this. This is where you have to say to the operator, don't be, well, if you put up a plant, you anyways have, any engineer's sense is going to safeguard for some reserve, no? For example, if your result is I need a tank for a 20-meter diameter, Okay, 20 meters, very easy. You have 315 square meter, right? Because it's P D squared by 4. No? And it's 400 by 4 is 100, and 100 times P is 315. No? So that's your square meter. Now, but if anybody who has a sense says, well, I'm going to make 24 meters. Let's take 25 because I know the square of 25. It's 625, no? And if you see the relation of 20 to 25 is by, and what is the difference? It's just 25 meters in comparison to 20 meters is just 125, at each end a little bit bigger. But you will have more than 50% of reserve. So, instead of building a 20, you're not going to build 25, but you're building 24. So you have close to 50% reserve. That's a lot. And the cost for that is going to be maybe 5%. Because it's only a little bit more concrete. What else does it take? No? So why wouldn't you do that? Get yourself 50% reserve. You can sleep very easily. 5% cost. Well, you get 10% of that anyways as consulting fees. So, no. Always put a little bit. There's people that just put too much reserve. No, that make things too big. That doesn't make any sense. But a certain reserve, and especially where it's a good idea. No. And rather, if you have problems with groundwater table or something, then you might not make it as deep, and but you still put yourself a little bit reserve, no? Normally you come up with maybe 0.35 meters in diameter. Okay, you can just buy it in 20, 22, and 24 because this is where they have the molds for that, no? So it doesn't make any sense. They've prefabricated molds, no? And that makes it a lot cheaper than making a special mold for that kind of garbage, no? And this is important that students learn that. That makes engineering life a lot more relaxed because something is going to happen while this is constructed. Someone they get a new factory or something. Those 50% reserve are gone after a while, no? And you're supposed to be safe for 20 years. And if not, no, nobody is really, no. They always are just going to come up to you if you made it too small. Once, they'll beat you up because it's too expensive, but they'll do that anyhow. No? When you want to sell something or when you present a project, it's always too expensive. No? This is always what in any project is. They come up, no, and when you ask them what do they want a Bentley or Rolls, no, and when you check them the price, they want a Fiat 500 or something, and you got to sell them an Audi or a BMW. That's what your job is, no? So you have this fight, and in those details, nobody's interested at the end. You as an engineer, you're responsible for that it works safely. No? So don't worry about what the people tell you. No, they don't mean it anyhow. No? Okay, this is blah blah blah. We're back here. Yeah, that was. Okay, here we were. So I think we have this now with the SRT. This is very important for that you really do understand that you have to read and try yourself and use the drawings I made to make it clear that you really understand it, because this is something you have to have in your mind, and you have to have well understand it and be safe in it if you want to design fermenters, no, of anything. Was two microbial populations. The growth rate of the slower growing population shall obviously determine the required SRT for continuous fermentation in a bioreactor. The faster growing bacteria, they will have a little bit hunger. You well can compare any fermentation with a buffet party, no? If you have more guests than you have food, then everyone is going to get something to eat, and they'll eat everything. No, if just a few guests come and you have a gigantic buffet, only salmon and caviar is going to be eaten, and maybe roast beef, and the potatoes and the vegetable and the bread is going to be over, right? And this is the same thing in our aeration tank, and we have to make sure that everything is eaten, because what's not eaten we have as pollutants in our effluent. So we have to make safe. We have to safeguard that we have enough bacteria, and by the final clarifier, we have to in an activated sludge plant, we have to safeguard we can hold enough bacteria in the system, no? So we really get our concentration. This is a little bit different if we talk about a fixed media reactor, trickling filter or fixed media. There, the bacteria, there we have to give safeguard. We have enough surface where the bacteria can grow on. Then we have sufficient bacteria in our biological reactor. Because they grow on the surface, this active surface area has to be sufficient. And there, the final clarifier has only one function, to take out the surplus sludge. Because we don't have any return sludge, but then we have the problem, or we have to safeguard that we get out the surplus sludge out of our bioreactor. For example, in a trickling filter is just a pile of rocks, really, or a pile of plastic material. And there you have, of course, you have to safeguard by hydraulic conditions that you flush it sufficiently to wash out the surplus sludge. Because if you don't do that, you get clogging and you get channeling, that you will have certain areas which are clogged, and then the water, of course, will always rinse through where the resistant is least. This is what water is well known for. And so if you have channeling, then you just don't have sufficient residence time for the water to be cleaned in your fixed media reactor. There is, of course, the extremes. One is the activated sludge plant, and I think we get later, shortly to that, to the trickling filter. That's the very opposite, and they have all kinds of mixtures. It's not sufficient time to really discuss all those mixtures with its advantages and disadvantages. And right now, the activated sludge plant is the most used system, and we'll get back to that later a little bit. Okay. The growth rates have to be determined taking into consideration FM ratios. Make sure you have enough mice to eat all the cheese, I always tell my students. That's an important part. These basic bioreactor design can be applied widely and are the basis of design of activated sludge plants for carbon and nitrogen elimination. Fortunately, nitrifying bacteria have a very low Ks value, so that growth rate of heterotrophic bacteria that eliminate COD and BOD by respiration can be reduced to be equal to the growth rate of the nitrifying bacteria by reducing FM ratio. Due to the low Ks value of the nitrifying bacteria, the reduction of the FM ratio of heterotrophic bacteria shall hardly affect the growth rate of nitrifying bacteria, although the reduction of the FM ratio applies, of course, to heterotrophic and nitrifying bacteria equally. The reduction of the FM ratio in an activated sludge plant is attained by reducing the specific volumetric load of the plant while keeping MLS as constant. The allowable specific volumetric load determines the required volume of the aeration tank of the wastewater treatment plant. Denitrification of the nitrified ammonium in the influent is attained by heterotrophic bacteria using the oxygen of nitrate rather than dissolved oxygen from the anoxic respiration of organic pollutant, as a COD, BOD. Using the oxygen from the nitrate for the respiration, the heterotrophic bacteria shall reduce the nitrate to elementary nitrogen. The problem with this is that the heterotrophic bacteria shall only use the oxygen of nitrate for the respiration if no dissolved oxygen is available. I think we have that on our table still. Let me remove the other stuff, and we come now back to this topic. We might leave this here, but we can touch out of this SRT here. Because we're not going to come back to this again. And we're not coming back to this again. This is all done. And we're not coming back to this again, or I will put it again on. Okay, we're back now to this problem of nitrification, denitrification. So the problem is, however, that the heterotrophic shall only use the oxygen of nitrate for their respiration. No dissolved oxygen is available. We have this as a condition for denitrification on the whiteboard. For nitrate being available for denitrification, however, the ammonia in the influent has to be converted into nitrate before. So, we can't make the denitrification in the head of the plant where we have the COD because we have no nitrate. While nitrifying the ammonium in the influent, however, all pollutants, COD and BOD, in the waste were eliminated by heterotrophic bacteria by respiration, especially because for nitrification we have a reduced FM ratio for the heterotrophic, so they're going to eat everything up because they are starving almost in the party. No? Due to the reduced FM ratio, the elimination of the organic pollutants should be rather complete, leaving almost no pollutants for the posterior denitrification. So denitrification thus needs nitrate, COD, and heterotrophic bacteria. The problem is upstream of the nitrification, COD and heterotrophic bacteria are present, but no nitrate. And downstream of the nitrification, nitrate and heterotrophic bacteria are present, but no biodegradable COD. Okay. Figure 17 shows the three basic process alternatives to solve this problem of a lack of COD after nitrification of the ammonium and the lack of nitrate upstream of the nitrification when COD is still present. For an upstream denitrification, effluent of the nitrification has to be recirculated into the upstream denitrification tank in order to supply nitrate to the upstream denitrification. Sounds nice, but it is actually the most nicest alternative. However, in order to denitrify 80% of the nitrate formed in the nitrification, 300% of the inflow plus the 100% of return sludge have to be recirculated. So we talked about recirculation and dilution of everything. In recirculation, however, the head loss is low because I have one water table and I need just to pump it back to the front end of the tanks, and I have between nitrification and denitrification, I don't have head loss. No, so it's only the Reibung, the friction of the pipes I have to overcome. So 50 centimeters of head loss is more than sufficient for the pumps. I might even have the tank organized in a U shape, and then I can just pump through the wall from the end the nitrate into the head of the pump. No? If I just make it a tank in the bird's view, like here, this is like we, for example, have it in Wismar. I have my inflow here, I have my effluent here, and then just through the wall, I have like propeller pumps, and I can make a backflow, a recirculation. This is how normally you do it. So this is how it works really nicely. And then you have here only stirred compartments. No? You can make it even by cascading a little bit, and then you start here with aeration. No? No. And have connect these to blowers, no? Have all the blowers here, supply then the air into the tank, no? This is more or less how you solve this problem. This is the most widely practiced solution which we have. No? And those three solutions, this is what you have here, and this is the problem. This is the upstream denitrification with the recirculation. We have here CD but no nitrate. Here we have, due to this recirculation, we have low nitrate, but there's no other way of doing it. Then we have simultaneous denitrification. There you have alternating aerated and stirred zones in a tank. This is normally what you also do in a closed loop tank. So you have just one zone which is aerated, one zone which is not aerated. You have an inflow into the aerated zone, so you nitrify, and then by steering this the circular or it's oval shaped, normally channel, then you have you finish aeration, and then you have on the back lane you have you just have no aeration, and there the denitrification is supposed to happen. This is not so easy because when you have a variation in the load, then you might not have a sufficient oxygen uptake rate in the transit zone after aeration, so that you really get down your oxygen in the denitrification zone. Because in order for the sludge not to sedimentate in this channel, you normally have to have a flow rate of 30 centimeters per second. So, and if you put a stirrer, and safety first, the engineer at the end of the day, you probably have a realistic flow velocity of 50 centimeters per second. So 50 centimeters per second in 20 seconds for taking down the oxygen concentration. 20 seconds, you have 10 meters gone. No? So how long is your channel going to be? How long is your transit zone? And 20 seconds is close. It's nothing, no? Because depleting the oxygen, if you have a low load and your oxygen is running in a minimum, you might have 4 milligrams, and you have a slow oxygen uptake rate. So this is why these plants became a little bit complicated. It started out with these plants because those, especially in Holland, those carousel plants were pretty well known, and they liked to use them. They were pretty simple from the installation, and you could also implement that in systems with surface aeration. With surface aeration, when it started back in the 60s, 70s, those oval ditch plants or carousel plants, like they were called in Holland, were pretty popular. But this used to be pretty complicated. Today, this is a standard solution. And today we can manage with a fine bubble aeration, which is more effective in the oxygen, as from the energy for the oxygen transfer, and with the rubber membranes, we are well situated that we have now safe diffusers which we can shut off very easily. So, and then we can automate the whole thing. Okay, now the downstream nitrification is something when you just don't have enough COD, no? When you have a problem, when you have an unfavorable nitrogen to COD ratio, as when the nitrogen is too high, then and you have to work anyways with external COD. But this is just only for fine tuning. For example, when you have very sensitive receiving water and you have to come very low with your nitrate, then you might have post denitrification. Normally you have a combination then of an upstream and a downstream nitrification. You just do the rest here, no? And uses then in biological filters. This is which we have a few installations in Germany, curiously financed by the Gazprom from Russia, no? Because they had, when you do something, when you do a construction measure that has any effect to the environment, you have to make an equal contribution to improve environment in another side. So those guys from Nord Stream 2, they just paid money to the sewage treatment plants to install filtration systems after secondary clarifier, and they installed biofiltration systems for removal suspensors and for rest nitrification and denitrification. And they pay, I think, 20 years of operation costs for the ethanol they are going to use there. No? So it's pretty costly. No? Well, in one of the cities in Stralsund, we have a big brewery, so you have a COD source there, no? So you can get really concentrated COD wastewater and use that as a for final denitrification once that is paid enough, no? So in simultaneous denitrification, wastewater flows several times through a sequence of an aerated zone and an unaerated zone. Simultaneous nitrification, denitrification is mostly realized in activated sludge plants with a circular flow, in a oval ditch or something, kind of constructed aeration tank, often insufficient oxygen depletion in the nitrification zone due to a high elimination of COD in the nitrification zone causes an incomplete denitrification. So this is a little bit the problem of those plants. And because the less efficient use of COD in denitrification, a larger volume for the activated sludge tank in comparison to an upstream nitrification is required for simultaneous denitrification. This is also respected in the design guideline. In downstream denitrification, external COD source is required. If acetic acid, ethanol, or methanol, as one of those has to be used as an external COD source, costs are not negligible because it really costs money. Methanol is the least costly of these three options, but most sensitive in operation because to get the bacteria used to methanol it takes a while, and the methanol has also is potentially hazardous to the environment. No? So some recent studies, however, seem to show that the potential of internal COD sources of the activated sludge might have been underestimated so far. At least I know from years ago it was that they wanted to make with post-denitrification because they wanted to substitute the final clarifier with a membrane equipment, and then they wanted to study post-denitrification there. And so they didn't come up with a methanol tank, everything else was ready. So at a certain point they just started, let's start with the operation, then we might not have a good denitrification. And to their own surprise, they realized that the denitrification was perfect. No? And well, if you really calculate how much COD you have in the activated sludge, it's so much COD because if you have 4 grams, we're talking grams MLSS, and you have a COD ratio, now you're 70% and 1.5 is about the same. You have 4 to 5, or anywhere between 4 and 6,000 milligrams of COD you have in your activated sludge anyhow. And for denitrification, what do we talk about? How much do you need? Well, if you have 100 milligrams, which you're not going to have, maybe you have 60 or 80 times 6, 360 milligrams. So if you can activate 10% of the COD of the activated sludge, it's well enough normally to get a quite decent denitrification. And that's what obviously the microorganisms do. No? They do have some reserve, especially if you push the plant a little bit. And if you operate decently. So I think this was underestimated. It shall be a good idea maybe to study it. And we observe in treating manure, we have some COD. Manure is not really rich in COD. It has maybe, but in anyways, you have 4 or 6,000 milligrams you have 15,000 probably COD total, which is low in comparison to the solids concentration of 10 grams or something, which you have. So most of it is digested in the pig stomach, but still 6,000 is a word, no? And 15,000 altogether, and that's even if you have 1,500 of milligrams of ammonia or 1,000, you have 1 to 6. You have the ratio for complete nitrification, denitrification. And we observe in the tank where we just want to nitrify, to produce nitrite, because we thought we had to install an Anamox process. Well, we come back to that. Let me read this because this comes in the story as well. Okay, have been underestimated so far. So these basic process alternatives have been completed, have been complemented by numerous process developments where you mix all those kind of different things. In these process developments, the three basic ideas, however, are combined with each other and with intermittent aeration and or alternating wastewater loading in one of the multi-stage processes. No? So you could just, if you have 3 tanks in parallel, you can have 1 in denitrification and 2 in nitrification, and then and have continuous feeding, or you even can have the feeding only to the tank who is in nitrification. No? It all depends. You can develop 100 ideas if you have multiple tanks, how you can combine those, operating each one in a different modus at a certain time, and combining this. There's infinite ideas, I guess. No? The most radical one of changing from this, what I've presented so far, because what I presented was the activated sludge plant in a through flow thing, where you have one tank after the other, and all the tanks you operate in steady state operation, with the flow going through every tank at any time. Well, you can do it just totally reverse. You can say, hey, why don't I just build 1 tank and I make it on a time scale? And I just, for a certain time, I use this tank for biological peer removal, then I use it for denitrification, then I use it for nitrification, and then I use it for sedimentation. This idea has been brought up also at the end of the 80s from the United States. It was an SBR, sequential battery reactor. I think South Africa and US were the ones that mostly started using it. And this is a very nice system, especially for industrial wastewater, if you have high loads, as organic loads and not so much hydraulic loads. Of course, the SBR is not optimized for hydraulic loads, but it's very optimal for varying organic loads, because you can, by the time, it's the same thing that you have, time. In the time you can change very easily by just programming a different time you're using, and that would be on a on this continuous flow thing. It would be like that you would be able to change your volume, but of course you're not able to change the volume of an aeration tank. How are you going to do that? No? So when you do a flow-through plant, you have to design all the volumes for the maximum load. In SBR, you can do it with time. If you have less flow and a higher load, you can just use more time. You can make less sedimentation time, more time for aeration. And even if you're low loads, you don't even use the whole tank, because you pump it anyways. No? In a through flow plant, you have always you have to use the whole plant, because it has a hydraulic design and it was overflow. No? Half filled, you can't use it really. No? Okay, so this SBR process is, however, sensitive in respect to strong variations in the hydraulic load, like for example stormwater, but it is, however, most adequate for wastewater varying not so much in hydraulic load, but in organic load. No? So if you have a mixed sewer system, but I don't think about SBR, you're just going to have problems with stormwater. If, however, you have a separate sewer system, or if you are looking at industrial wastewater, SBR might be an interesting option. For the denitrification to work efficiently, biodegradable substrate should be available. As denitrification with oxygen from nitrate is energetically less attractive for the heterotrophic bacteria than respiration. It works, and I think we're well over time. But let me finish this point here. Is energy less attractive to heterotrophic bacteria than respiration with dissolved oxygen. Under optimal conditions, the rate of respiration in denitrification is only 75% of the rate of respiration with dissolved oxygen. This is what you have to consider when mentioning the volume for the denitrification tank. But in order to overcome the problem of lack of COD for the denitrification process for wastewater with high rate of nitrogen to be denitrified, and to COD with only nitridation and denitritation, and processes with partial nitridation and anaerobic ammonia oxidation, called ANAMOX, have been investigated and are beginning to be established in practice. These processes are interesting for ammonia-rich wastewater as they are filtrates from anaerobic digester effluents and manure, because manure is a very big problem, and here we're talking about something that has to be developed in the near future in order to protect our groundwater. The anaerobic ammonia oxidation, ANAMOX, is a microbiological catalyzed process which is used in reducing nitrogen oxides and waste gases from power plants and automobiles. What you buy with AdBlue is just your pee-pee, no? It's just your urine, it's the same thing. You can also pee in that tank and it'll work fine. And in your car, and this is a catalyzed process under forced reaction conditions, because waste gases from your car and from power plants are pretty hot, like 500 degrees Celsius or 200 degrees Celsius, whatever can stand the catalyst. Okay, and this is something for you to look at now in the break. This is conventional chemical equations for nitritation, nitratation, denitrification, denitritation, and ANAMOX. The only thing I want to highlight is you see here, if you in nitritation already acid is generated, so buffer capacity is consumed, buffer capacity or alkalinity is consumed. You need oxygen. In denitrification, by oxidizing carbon, you recover oxygen, which else you would use for oxidizing this carbon, but not all of it, because the load of the oxidation number in ammonia is -3, and in denitrification, at the end of the day, you have ±0. So, but if you go to nitrate, you go from -3 to +5, and you come back to 0. So the 5 electrons you recover, and the 5/8 of the oxygen you recover, and 3/8 of the oxygen you have to invest in order to get in nitrification, denitrification, in order to get to the pure nitrogen. Okay, in denitritation, you just make a shortcut, but this doesn't change really anything about the hydrogen nor about the really the oxygen. It's just you need less COD. So if you have sufficient COD, it's no problem, because if you invest the oxygen to oxidize COD, or to oxidize first ammonia to nitrate and use the oxygen from the nitrate back, but it doesn't make any difference to you economically. But it might make a difference if you just don't have COD, because then you have to buy COD to be oxidized by nitrate, which you first have to oxidize. Also, you have to pay for that, so you pay twice. Then nitritation and denitritation might be a good choice. However, you have to look at, if you work with nitritation only and denitritation, you might get a problem with N2O, which is very climate affecting, because it has a climate factor of 240 in comparison to CO2. This is very climate, and so you should have a very close look at that. The same is true for the ANAMOX process. In the ANAMOX process, you only produce 50% nitrate, and then you combine nitrite with ammonia and produce your nitrogen. Exactly, you can have a pure ANAMOX process, because bacteria shall always produce in the ANAMOX process about 10% of nitrate. That's what you have to do. Okay, this is here, and then next here, let us make here a break, because then we start with a short new topic. But I think one more lecture should be sufficient to that we get through with this. Okay, thank you very much for this. For your attention so far, and let's meet at 11:20. No?
Sounds like a plan.
Good. Thank you very much. Okay. Let's get a coffee and then we'll read you and then we'll be. Yeah, we're working and trying to get this NMOX to treat manure.
Ammonox is something I don't know a whole lot about, but the more I hear about it, it's come up with a lot of really fundamental questions that really need to be sorted out.
That might be something we might consider. I'd like to think about
Yeah, because I mean, what always gets me is, like as a microbiologist, heteroatoms, nitrogen and sulfur, always very, very important. they would get a PhD. Oh, I think, it hurts me to hear that she doesn't want to do a PhD.
Yeah. But she doesn't, no?
She doesn't seem to want to know, and I mean, it's just, you know, I know she's been fantastic, hardworking, intelligent,
Yeah.
puts things together.
Yeah.
She's a good puzzler, you know, she fits things together.
Yeah.
She's the kind of people that should be in PhD programs.
Yeah.
Instead we get people that have no business.
Exactly. It's hard to find someone who's appropriate for PhD. It's not that easy anymore. No? Because people want too much at the same time. No? Also for her, I can understand her life plan. No? It's different and okay, makes sense for a woman because it's very well compatible with family, what she has in her mind. No? And okay, that's we don't have any right to screw up someone's life. That's not our job as a professor. Should help them to get in there. Okay. It makes anyways. You know, university education is good for clear thinking, but there would be more potential, which we unfortunately can't dig up.
Yeah, and I mean, it's just, what I'm finding more and more is like, I've had a couple master's students from Europe, and like, a few students from Scandinavia in particular, one from Finland, and just the amount of entitlement. I mean, you know, not only do they expect to come into a project, they want to be well paid, and they want to be able to take up and leave for 6 to 8 weeks, you know, with no questions asked. You know, it's like, what do you think this is? You know, it's,
No, those people don't come up. You know, this is a nice thing. Once when there was still a diploma, the people had to decide in the 4th semester which line they're going to follow. No? Solid waste, process engineering of renewable materials, or water and wastewater. No? And so once I was in this course of chemical separation process early done, and there was one student from the 6th semester because he hadn't passed it. No? So I said, okay, you guys can ask him now, and I packed my stuff and go out, and so he can deliberately talk. So he stood up and said, you don't have to go out, everybody knows. If you want to get bad notes, if you want to work hard, no excursions, you go to Professor Pfeiffer. The only thing is you get a job. You get a well-paid job. If you want excursions, if you want that, you go to the other ones. That's it. So, you know, it's pretty well known what you have to expect. So I never have problems. The people that show up with me, they know they have to work and they want that. No? That makes, for me, life a lot easier.
yeah, no, that's really good, you know.
Yeah, once your name is ruined, everything is okay. Okay.
I do work a little bit harder.
Okay, we're back in business here.
Yeah.
Anybody listening?
We had two a couple of minutes ago. Looks like they were idle, but I will just keep going.
Okay. Anyhow, welcome back in business here. So we'll start with the last session here. And the new topic is because we have one topic left, is the phosphorus removal. But in between, we'll talk to what I mentioned, system with suspended salts and system with the sealed biomass. Because that's the two alternatives. Because if you want to treat wastewater and a lot of other biotechnology processes, it's important you decouple hydraulic retention time and salts retention time. Because your growth rate of the microorganisms is lower than the reaction rate. So that means reaction rate is how the substrate is converted into your products. And that might go faster than, also has to deal with this yield coefficient. You get more products and the growth rate is not that much. So then you get your product, so you have to separate the product from the bacteria. And if the bacteria don't grow fast, you have to keep them in the system or you have to return them to the system, right? So there's the two ways. To separate and return them is when you work with suspended biomass, and to keep them in the system is the sessile biomass. In both cases, whatever you have is a yield, because normally what you want is you have continuous and discontinuous fermentation. In discontinuous fermentation, it's a different thing. There you grow your feed batch systems. I think that has to do with batch, is that you grow up your microorganisms, and finally you quit the batch and you separate them, and you might use some of your bacteria as inoculum for the next feed batch or batch. And but then the surplus you just dispose of, and it's a discontinuous process. There you of course don't have any steady state conditions. You have dynamic conditions. You have to deal with a differential equation to describe that, but simple differential equations. And there's a growth curve. You have a lag phase and you have an exponential growth phase. Then when the food is declining, you get a growth rate will decline to 0. And finally, if you wait too long, you after starving, you might get a Louise's phase where microorganisms die away or decompose. No? And but this is not what we're talking about, because these feed batch and batch systems are mostly used when you have to work with a sterilized and sterile environment, and you have to sterilize it, because to continuously sterilize is quite difficult, and normally even up to now penicillin, and there's only 2 plants I think worldwide producing continuously penicillin, and they don't operate all the time because they give so much hassle. So for sterile biotechnology, I think continuous processes are virtually non-existent. Might be a few. I'm not that much in the system, but it's virtually not. No?
I certainly don't know of any on a large scale.
Oh, okay. Now we talk, if you don't have to work in a sterile environment, then you can work with continuous cultures. We, of course, in wastewater, we want not to work in sterile because we don't have any preference on the microorganisms. We want to have the microorganism diversity as wide as possible in order to that the different microorganisms can cope with anything that comes. No? Because we want, no matter what the substrate is, we want to degrade it. No? So we are friends of diversity, and we will do a hell of a lot not to exclude anybody and not to have a monoculture there. We are interested in having most diverse culture because we have a diverse substrate we have to deal with. So in continuous cultures, in any continuous process, you want to have steady state conditions. Steady state means that parameters don't vary with time. And this is especially what our mass in our system is. So we have to take care that that we just take out what's been grown, and that we conserve everything in the reactor which is not covered by growth. No? So to keep the mass in the reactor constant. This is a problem we talk about now. So alternatively to the principle of activated sludge process, which is recirculating the suspended microorganisms after sedimentation and thickening in a secondary clarifier for decoupling HRT and SRT, this is what we're talking about. Also in the last years of the 19th century, the trickling filter was patented in the UK, decoupling HRT and SRT by growing sessile microorganisms on fixed media in the bioreactor. Initially, the fixed media in trickling filters were fist-sized basalt rocks, which you have enough of in Iceland, with a specific surface area of some 100 square meter per cubic meter. Meanwhile, a vast variety of plastic media and other media also, but mostly plastic, was up to 600 square meter per cubic meter. Specific surface area have been developed in numerous processes combining suspended and sealed microorganisms with submerged and semi-submerged, fixed and moving carrier materials have been developed. This vast number of processes alternatives, however, does not change the basic principles. For suspended biomass, it is important to settle and thicken well for the effective recirculation, so that the biomass is settle and thicken well for the effective recirculation. Then it's easy to separate the amount of surplus sludge by the gross. You just have to measure the MLSS, and since you have a large amount of MLSS, it's good if you measure it daily, and then you adjust your surplus sludge drainage of the system according, because you know the concentration, and so you just say the volume. There you can more or less keep it, sludge volume and MLSS. This is what an operator has to look at. In an SBR, it's even simpler, because after sedimentation, you just pump away the a certain amount, and you just have your pump at a certain heights. So whenever the level of the surplus of biomass is over the pump, it will pump biomass, and if you don't have sufficient growth, so it pumped away more surplus sludge than you should have, then you'll pump just pure water. No? The pure water will return as filtrate from the surplus sludge thickener into the process, so nothing is going to happen really. No? That's how simple you can do that. You can do the same thing more or less in a continuous process when you keep up the sludge level in your final secondary clarifier. It's not really being practiced that way, because to keep up the level, what's now been done is measure the level of the surplus sludge in the final clarifier, because you just put an optical sensor from the scraper, and the scraper is just turning around. So the only problem you have to get the signal from the scraper that turns around through an electric condition, which needs to be flexible because you turn it always around. But this is an electrical problem which you can by contacts as a I don't know,
Swivel, what's it called that? I can't remember the English word, but yeah, I know what you mean.
right.
Yeah.
It's by friction. No?
Yeah.
You have friction contact, electrical contact. That works. That's a solution now, which is well practiced, and you don't have any problems with that. Since you have very low as a low voltage, low current, it's easy to manage. You know? And but or you can just look daily at your measurements and adjust your drainage volume for the surplus sludge, you know, of the pump. How long do you want the pump to run? You know? And more difficult is it to control it in a fixed media, because you're not going to really you can't really look into the fixed media, because you have a pile of stones. How do you see what's inside? There's no way. So you have to flush sufficiently to make sure you don't have any accumulation of sludge and channel building in these fixed media beds. If you have that, you have to empty everything. And if you've done a good job, you really have to do it with a Presslufthammer. I don't know, this hammer was compressed air hammer. Or,
The concrete breaker.
yeah, concrete braided thing. No?
Jackhammer.
A jackhammer, right? That's a word for it. Okay, and for that reason, this plastic media with 600 square meters per cubic meter, don't use it for wastewater. For wastewater, stick with 100 square meter per cubic meter if you have wastewater that still might have some suspended solids. Only if you have very low concentration of suspended solids, maybe in case of industrial wastewater, you can go up to 200. But you shouldn't go up more, because be on the safe side and rather build it a little bit bigger. In many of the developing countries, they like to have those high surface, specific surface areas, and then they wonder that after 6 weeks, the thing doesn't work anymore, because the pump breaks anyways down, so they don't have sufficient flushing, so it's all one thing. And another problem might be lipids, fats and oils. It's very easy to make out of what we say fixed media. In German, it's called Festbed, and grease is fat. It's very easy to make out of Festbed and a fat bed. So you just have one chunk of fat and oil. No? And that's, of course, not going to operate anymore properly. No? If you have that, you have really, it's nice, because If we're talking about technical installation, you get those blocks which are about 70 high and 50 by 50 centimeters. So they have a volume of 5 by 5, 25 by 7, so 175, not 7, 8, yeah, 775 liters void volume. No? The void volume of this thing is normally 95% or something. There's very little plastic in it. It's 5% only, so it might be 7, 8 liters of plastic. So the whole thing doesn't weigh much, because it weighs maybe 7, 8 kilos. It's very easy to change. You put it in your wastewater treatment plant. If you want to remove it, it might weigh easily 100 kilos. And then this plastic stuff isn't even going to where you're going to grab it, because it all falls apart if you have 100 kilos on it. So this is not, as a handling of those fixed media is not that simple, and be on the conservative side, please, if you use that. Okay, for suspended, okay, we had that. For Cecile, for suspended mass, it's important to settle and sticking well for an effective recirculation. For suspended biomass, bioreactor and secondary clarifier are one system. They don't work independently. For Cecile biomass, clogging and channel forming in the bioreactor is a main problem, and it will be a problem. Believe it or not, you'll learn it no matter what your decision is. Clogging and channel forming has to be avoided by avoiding excessive specific volumetric surface areas of the carrier material and the effective hydraulic design. So safeguarding that clogging and channel forming is avoided. So stick with 100, mostly 150 square meters per cubic meters. You'll be on the safe side and have regular flushing. With suspended biomass, settling characteristics of the biomass play, with suspended biomass, settling characteristics of the biomass play a key role in the entire process. In system with sessile biomass, a secondary clarifier separates the surplus sludge and attains thereby almost 50% of the treatment efficiency, but there's no effect on the performance of the bioreactor and no sludge is recirculated. So that means you do have to look at the secondary clarifier also with 6 media, because 50% of your pollution is assimilated in the biomass, in the surplus sludge. So you have to have the surplus sludge. You have to separate the surplus sludge from the clean water, because if your surplus sludge is in the clean water, you have contamination in your clean water. Your treatment efficiency is going down significantly. The potential of the surplus sludge is 50% of your pollution. So be careful with that you get rid of your surplus sludge. And even in the 1920s, the forefathers of the wastewater treatment, Mr. Imhoff, and the old Imhoff there, to be a grandson with the same name, he published a book, and this guy always said, a treatment plant, a wastewater treatment plant without a sound sludge treatment plant is worthless. No? A wastewater treatment plant without a sound sludge treatment and disposal is worthless. So if you don't know what you do with your sludge, don't even think about building the wastewater treatment plant. No? You have to solve the problem of the solid waste generated in the processes. No? I recently had a guy, I think I told that, from Peru calling me. They have a biological system for treating cannery waste for vegetable cannery as wastewater from vegetable cannery processes, and they claimed they had too much fentanyl due from the paprika and this kind of stuff, and they want to put a DAF in front of it. So asking, well, DAF is not the problem. What do you do with the sludge? Because if you have a aerobic treatment system, you get your surplus sludge. Okay, you can put that on fields. If you have sufficient aeration, it's not even going to do you any hassle. And of course, they have in Peru enough land to put it on. Might put it in the desert. You're doing something good. But what are you going to do with flotation sludge? That's not stabilized. You can't even transport it. We had that, even in Germany, they invested 600,000 euro for a dewatering plant, and the dewatering plant is not the problem. That's done with maybe 200,000 investment. You have a screw press for dewatering the flotation sludge, and works fine. You get a sludge comes out, and it has a consistency. They can put it on, and you can shovel it, so that's all okay. And then you put it into then the other 400,000 you need, because handling of solid waste is always pretty expensive, because you have screw conveyors to get it into the truck. As it's an open, how do you say?
Flatbed truck, like it's open.
Yeah, yeah,
Yeah, like the dump truck, but not a dump truck.
yeah. It's how do you say? Mulde, is it called here? Pooh. It's a tray, travel trays on it. Depression, swale, scrape, recess, skip, hollow. No, it's like a hutch, is that it? Hutch truck? That's not good. But you know what, a tray, or what
Yeah,
do
it's
you,
like the flat ones.
it's like, no, it's not flat, it's like a tray, like where you put in pig food, just over dimensional. How would you call that? If you have a tray? Trough,
yeah.
a trough truck,
Yeah,
You have a trough truck for 20 cubic meters, you can put in the sand, or, and sand is nice, you put it in there, and sand normally won't move, no? But if you put in this stuff, you can shovel, anything you can shovel, normally you put it in a trough, and the truck can run with a trough, no? But if you put this stuff in a trough, especially if you have summer, if you wait one day, it's all liquid again, no? Because it's first of all, it looks like, pretty, like mud you can shovel, but it looks stable, but wait a day, and it's not any more stable, no? It becomes more and more fluid, no? And so if the truck goes on the road and he has to stop, it's all on the road, no? The sludge, no? So if the truck driver says, I don't care what you do with that stuff, but I'm not gonna transport it to anywhere, and then you have a serious problem, no? Because the guy with the tanker is not gonna take it either. He says, I'm not gonna get it nor in nor out of my tank. So if something, you can't transport it in a trough, you can't transport it in a tank, and nobody wants it because you can't handle it for a biogas plant, no? So they have tried this, and they've retried it, and it has always been a problem, no? Always some company shows up and says, we're the champions, we can do it, and it's not gonna they take 20,000 euros for making experiments, and sometimes they produce something, especially they like to show up in winter. In winter I can do it also, no? Because you don't have to do much if it's really cold, no? Because then biological processes don't go that fast. But whenever your temperature rises to 10 degrees centigrade or above that, and that's normal in Germany, then the microbiology is quick, and within a couple of days you have liquid mud on there, and nobody's going to do anything with it, no? So this engineer was responsible for putting that. He always tries it again, and I told him, wait till we have the biogas plant, because then the biogas plant, that sludge that comes out of that, you can put in your press, and you can put in your trough truck, and you can haul it to an incineration plant. It's a lot less, but then your dewatering plant is going to be getting use. Half size or quarter size would have been sufficient at that time, but okay, never mind. It's there, so we can use it. So again, the sludge, you always got to think the solution from the sludge. This is also something, if you don't learn anything else, next to this bacterial philosophy that the bacteria want energy, is think things back from the sludge. If you don't have anything you can do with the sludge, don't start with any solution. You have to find a solution for your solid waste, for your sludge, as long as you don't have a solution. Because I think in this cannery, if they put a DAF, they're not going to have a solution for the sludge, and they're going to put it, and after half a year, they're going to bypass it. No? So it's an investment they can sell to a museum or something. When we were PhD students, we always said we had this art exhibition in Kassel called like modern artists like Beuys and those guys were exhibiting their installations, no? And so what it's called? It was every 2 or 3 years. No, in Kassel, it was very famous. No, it was world famous. No? And this artist Beuys, he once sued the government of a state of Germany, of one of the states, because a cleaning lady took away fat that was put in a corner. It just was just fouling there. No? She thought it was ugly, and he said, it's an artwork, and I want 50,000 euro, and he got it. He got it. He sued, and he got those 50,000 marks back. No, totally crazy. No? And this kind of installations, no? There was all kinds of installations nobody understands. And so we always said, if you make a pilot plan, or if you make an experimental plan, make it with bunt, as always, colorful. The most important thing, makes it colorful. So if it doesn't work, you can give it to that art exhibition. You might get more money for it than you ever could get with your experiments. But important, it has to look crazy, and it is and very colorful. No? Don't make it boring. No one wants it then. No? Okay, now back to the serious things here. As with suspended biomass, clogging and channel forming is the issue for suspended for sessile biomass, and sessile biomass normally has very good settling properties because it's grown it grows to the carrier, and it's only washed away if it has a certain thickness, because then the shear force will take it apart. As there's two effects how the surplus sludge will be generated from sessile biomass, and when it grows thicker, there's two effects. One is that oxygen doesn't get any more to the core, so it's become anaerobic, and they will eat up those polysaccharides, which are really the glue that glue it to the fixed carrier. So when they eat up the glue, it's easier to fall off. And the second thing, when it gets thicker, also the shear force from the water is getting stronger. It's for the thickness of the moment to take it off. No? And so you normally the surplus sludge from fixed media is going to be like chunks, and of course those chunks have a better it's compact chunks, and those compact chunks have better settling and thickening properties than you have from suspended biomass, because in suspended biomass they want to go as volumetric as possible in order to have access to the food. No? So you need the flocks want to have a great surface. However, you can train them to have a small surface if you apply shear forces and select for the better settling bacteria. There's new processes that try to work with granular aerobic sludge. No? This is probably also $1 billion baby if you get that process stable. There's now a few companies, basically all of the first successful research was done in Delft University. They have now most of the patents, and also first research was done in Technical University of München by Eberhard Morgenroth. He's now with the EAWAC in Switzerland. And after 15 years, they start now going into full scale with these granular aerobic sludge. This is going to might be a revolution, an upcoming revolution in wastewater treatment, because in anaerobic reactors, this granular sludge was invented in the 1980s by Professor Lettinger from the University of Wageningen, also in Holland. And those USB reactors are now make up more than 80% of anaerobic treatment plants for industrial wastewater. They have been modified in different processes, IC, integrated circuit process, and there's other names for that. The basic principle is the granular anaerobic sludge. This we know since the 80s, and there has been a fantastic run when I was a PhD student, and has been a lot of problems. First was growing those anaerobic granules, but this is now pretty well known to the companies that offer that. That comes all from two companies, Gies-Bocardis and no, I just had it in my tongue, the name of it. It's gone. The sugar company that sold it, that made it, a process company out of it, was P something, it'll accumulate later. Those are which have most experience, but even in the small state of Mecklenburg-Pomerania, we have now 4 of those reactors, 2 in potato processing, 1 in a brewery, and 1 in milk, as in whey processing, actually. And there are paper processing and breweries, sugar companies have those USB reactors, starch companies have those USB reactors. As anybody who deals with carbohydrates has it, because they don't work for fats, and if you have fats, you don't get those granules. That's still a problem. Slaughterhouses and all the packing companies, you can forget, no packing houses. Now in the aerobic, they also try to get this granular sludge. Then this would be the ideal combination of suspended and fixed media, because then you have the stuff you grow on is your own nucleus. This is bacteria. Bacteria grow fixed on bacteria, because then you can have the settling velocity might increase from 1 meter to 60 meter per hour. So you then forget everything I told you about secondary clarifiers, because then secondary clarifiers will not be a problem. You will be able to integrate them. You will hardly not see them, and you will be able, with 3.78 grams MLSS, you will be then able to easily to increase to 30 grams, and also the required volume for your aeration tank will be just 10% or maybe 15 or 20% of what you build now. So specific costs for wastewater treatment plants will decrease by a factor of 5 or something. It would be incredible. And if you consider that in China, still about every week, a plant for at least 100,000 PE is going into operation, about every week, and that'll last for the next 50 years before everyone is connected, or you have a 80% connection in China. You still know what the market is. No? And then you can talk about India and the next country to come, no? Or Indonesia. So there's sufficient work to be done still. So this would be really something humanity could very effective improve wastewater treatment. So this really merits more research, but it's on its way. So this is something really to talk for the future about. Aerobic granular sludge is one of the things that we have to look about. Okay. Now, trickling filter system facilitate a very effective aeration due to the stack effect. Oh, yeah, I know, one more point I was going to make, because another development that was done 20 years ago is the membrane reactors substituting secondary clarifiers. This is not going to work. This is a dead end, and this is why it's important to also mention this. This might be something that only if you have space is very expensive. For example, on ships, on airplanes, and on space vessels. No? There you might work with membranes, but normally it doesn't make any sense, because they are pretty sensitive. It makes sense if you want to reuse the water, but then it doesn't make any sense to optimize the aerobic system, because when you want to increase the MLSS by membrane systems, there has been a fantastic PhD thesis of a guy named Günther at the University of Stuttgart, because he measured the alpha factor for aeration was increasing the sludge, as the MLSS, from 4 grams to 30 grams. Well, he found out the alpha factor decreases from 0.7 to 0.15. So that means the alpha factor is giving you the required oxygen supply. You have the alpha factor is the oxygen transfer in clean water to in wastewater to clean water. So that means in normal wastewater, you have about 70% of the oxygen transfer in comparison to the oxygen transfer in clean water with the same installation, same system. Right? Because if you buy a system, if you buy aeration system, the provider and we talk now in modern times about fine bubble aeration. So his system gives you the size distribution of the bubbles he's generating by his system. This is supplier dependent. Depends on how he slits the membranes and so on. And also it depends how you have the distribution of the inlets, so over the floor, if you get mammoth pumping effects or not. So this is system dependent. And so what you do is you ask the supplier to give you a guarantee on the oxygen transfer in clean water. Because he has to give that, he can test that in a tank, and then he makes an installation. And this is often done that in an installation we fill the aeration tank with tap water, we add a little bit cobalt for having, it's like working a little bit like catalyst. Then we add sodium sulfide in order to keep the DO, so the dissolved oxygen concentration, to 0 until the system has gotten into steady state and starting on lowers. And then we measure the rise of the DO over time. And from that we can calculate the oxygen transfer rate. It's called, determine the KLA value of the aeration system. The curve is it's an E function, and the exponent of the E function is a KLA factor. No? And that's A is for specific surface, and K is the oxygen transfer coefficient, and that depends on the hydraulic conditions which are around the bubbles. And then this alpha factor is wastewater specific, because that depends on the surface of the wastewater. That's on the bubbles. That's how you can measure surface active substances are going to absorb, and they of course inhibit the oxygen transfer. It's like putting insulation around the bubbles, preventing the oxygen transfer. And this insulation is affecting the K value of the system, and this is what we grab with the alpha factor, the difference between wastewater and clean water. And so now, if you rise you have to supply in 70 in comparison to 15%. No? If you divide that, you get a factor of 4 or 5 to 6. Sorry. What you have to supply more oxygen, and since the oxygen supply is 80% of the operation costs of the wastewater treatment plant, or at least 80% of the energy costs, and that's most of the operation costs next to or before sludge disposal. Then that makes really that's a very significant factor, and that was dead for the membrane technology and domestic wastewater treatment, because nobody is going to accept 5 times energy consumption. And now with climate and energy conservation, it doesn't make any sense at all. No? So this is a dead end. But if you have granules, those granules are compact, and the water in between is not affected. By concentrating the flux You just get, you influence the viscosity. And so if you influence the viscosity, it's obvious because if you have a suspended sludge concentrated, and you can see that if you thicken the surplus sludge, that it affects right away the viscosity. And this is obvious. If you see a sludge with 4 grams or with 30 grams, the 30 grams is like almost, it's like surplus sludge thickened, not in a machine, but in a tank. It has it has a much higher viscosity. And then you can, that of course affects the oxygen transfer rate. And then you have all this, the other particles are like sand, not because this granule sludge is just very compact. That's why it has such a nice, it has a high density and it's compact, and that's why it has this high sedimentation velocity, and so it's not going to affect the, it might even have a positive, you might even get a better alpha value than 0.7 with that stuff. No? So it's a really interesting development. Okay, now let's come back to this, what's written here. This is future, this is something for the next generation to work with. As a triggering filter system, facilitate a very effective relation due to the stack effect, because by stack effect is that you have a difference in temperature of wastewater and air, and so the air is cooled or heated, no matter whatever the temperature is, and 4 degrees difference is sufficient to give you an airflow of about 18 meters per hour, which is not very much. It's very little flow, and then you can, then you have to have openings on the bottom, and the top is anyways open, and these 18 meters per hour will give you an aeration which is much more than you will have in an aeration tank. So it's always as sufficient in a trickling filter, and you don't even have to pay for it, nothing. You don't even have to have a ventilation system. No? This is by natural force, and of course it doesn't cost much money to pump the water up the trickling filter, because pumping water is much more energy efficient than compressing air. And this is why trickling filters used to be, before nitrification, denitrification was obligatory, it used to be a nice system. There was many of the trickling filters around. There's still one in the UK, use a lot of those installations. But with nitrification, denitrification, they almost vanished. Because denitrification, it's such a good aeration system, the trickling filter, it's so difficult to get the air out of it. So it's so you almost got to have a submerged system in order to have a denitrification. A friend of mine, he says, I'm going to make a combination, and I'm going to make a trickling filter, and I'm going to make it that I can flood it. This is probably the only way you can really get a trickling filter to denitrify, when you flood it completely. If this system is going to, I think it might work, and for certain things, because it's also the Cecile microorganisms. It's not only that they have better settling and thickening characteristics, and the aeration is so nice because it's done by natural airflow, and you just have to pump the water. A third advantage is that the microorganisms, by the polysaccharides, are protected. So they are much more resistant against fluctuating loads, and due to the polysaccharides, they have also a certain substrate reserve. So for example, if you have a convention center, or if you have a restaurant out in the forest where only on weekends people come up, but then they come up a lot, or if you have a museum that's only there where you have very fluctuating visits, like castles, on the weekend everybody's there, in winter nobody is there, then those fixed media, Cecile microorganisms, those systems are much superior to systems with suspended biomass, because the suspended biomass will decompose, and their settling properties will be influenced, and also when you have we have in municipalities where you have a lot of tourism. And then you have very varying loads. It's also, and you have a lot of night, you have especially a low or high nitrogen to COD ratio. They also proved that trickling filter systems are more stable. Because normally in springtime, when tourism comes up and temperature changes, we have problem in all those touristic municipalities. Okay, as a trickling filter system facilitate a very effective aeration due to stack effect. Pumping water is much more effective than compressing air. This effective aeration, however, is a problem for denitrification. Due to this problem, trickling filter almost disappeared in domestic wastewater treatment from the 1980s on. Scientifically, and for the understanding of basic and chemical engineering, the fundamental difference in kinetics of activated sludge plants with only suspended biomass and trickling filters with an effective biomass is of great interest. It's really interesting, and it's nice to torture students with that, because activated sludge plants are close to an idle CSTR, which continuous tank reactor, and there you have to know that the effluent composition is the same as the composition in the tank, and the influent composition is just has no significance for the composition and concentrations in the tank and in the effluent. This students always have to learn. They always keep forgetting that. And the trickling filters are, of course, very close to idle plug flow reactors. And there you even can find that in the upper part you have heterotrophic microorganisms, in the lower part you find the nitrifiers, because first, of course, the heterotrophic have a higher growth rate, and then lower, when the COD is less, then the nitrifier become dominant. And you can see that, you can isolate those. And of course, you have what you do is you have to dilute in a trickling filter. You have to dilute the wastewater, the inflow wastewater, because you have just a chance. You run through, and the effluent that trickles out of the bottom of the filter is what goes into the effluent, because it's only separated the surplus sludge you wash out, and that's your effluent. So you have to dilute until you have exactly the property which you need. But this dilution also helps you to get a sufficient hydraulic load to flush out the surplus sludge and to keep it away from channeling. No? This hydraulic design is similar. We had once a survey on, this is again a little bit pain in the ass, because at least in those very small units for households, in order to make the hydraulic, or to have a proper hydraulic load on the trickling filter, you needed so much pumping energy that it was more energy in comparison to an SBR plant for aeration. Because the SBR plant, because all those for those very small plants, for just one household, or for domestic plants, as what we call decentralized systems. In Germany, they are just only up to 50 PE, and sometimes they are only for individual houses up for 5 to 10 PE. No? They are, of course, because they have very variant loads. Because if they have a party, or if they are on vacation, or if they have a few guests, and of course everyone in the house is doing the same thing at the same time, so they have a load variation during the day that's much higher than what you have in a normal sewage treatment plant. Now, a trickling filter is a flow-through plant, so you have to deal with all those extreme things. That's why you have to design pretty much. In an SBR, you have, since you pump the wastewater into your aeration tank, you have an equalization tank. So all the aeration you design for equalized wastewater. And then you're more energy efficient with, although the system of compressing air is so inefficient. Yeah, because you have a trickling filter is a through flow process. That means you have to take the wastewater the way it comes. And in the morning, everyone showers, so you get a peak load. So you've got to design for the peak load. So you have a bigger system. Now, with a bigger system, you have to guarantee that even in low load, the hydraulic load is sufficient. So you have the recycle pump has to run 24 hours a day, and is designed for minimum for the night. For the night, you have to flush still, because you have to flush all the time. So the flushing, it just runs through because it's too difficult to design that. And in SBR, you have also bigger tank, but you use most of it for equalizing the load. And your aeration tank is rather small, and your oxygen consumption you design for average, because you have the equalization tank in front of it. Yeah? And so that makes a difference, at least in practice that proved, because we have an experimental field where we have the different systems of this plant treatment, where they do it with the soil filtration systems with plants on top of it. The plants are not important, the soil filtration does it. There's also some specific which you have to respect. SBR plant and trickling filters and submerged fixed media reactors. So we have 6 different plants in practice, and I expected the trickling filter to be the most efficient one of the technical plants, and proved to be the most inefficient. I was also surprised, and also surprised was the supplier of this plant. So he came 4 or 3 times and tried to optimize the recycle rate. But whenever he was at a comparable level to the SBR, the plant would start to give problems. So at the end of the day, he had just to keep up this high recycling rate. Then the plant was running perfect, but then he had the highest energy consumption. I was surprised. He was surprised. He couldn't change it, and I had no idea how to change it. Okay, now this is something I don't want to fix now. The last topic, the pre-last topic we have to deal with is biological phosphorus elimination. Biological phosphorus elimination is a 2-stage process. It's microorganisms perform this 2-stage processing, having growth advantages by getting a better access to the substrate due to metabolism under anaerobic conditions. In the following figure, the process is illustrated. So we have here the 2 phases. We have here the phosphate release under anaerobic conditions. And the effect of that is that the microorganisms have built up polyphosphate storage vasculars or something. You can even see it in the microorganism, the Kellerin, and they build those up. And some bacteria, or I think a bunch of them, no? Most are able to do that if it has an advantage for them, and they learn how to do that they make this polyphosphate storage vasculars. And when they are then periodically change it between anaerobic and aerobic, this is when they try to build up this capacity. And if they have this phosphate storage, they can release the phosphate, and that gives them energy. With this energy, they can get the nicest substrate, the good biologically degraded substrate, and store that in so-called PHB vasculars. And this PHB is also, you can use it for making bioplastics and all this kind of stuff. This really is a nice chemical, could be a basic chemical for chemical industry. And also the bacteria can use it, because once they get into aerobic, they have this substrate, and so they can really grow on that substrate, and it's due to that they can, it's like a cold buffet. Some have their food box with them, and first you get in, you're not allowed to eat anything, and so they grab the nice food, and then at a certain time when the buffet is opened, everyone can eat, but they have already the nice food with them. And the other ones have to stand in line and wait, but they can start eating. And when the line is less, then they come up to a free buffet and get get the same food as he has, because the good food is anyways gone. No? And this is how this system works, basically. And then again, it's stop, no? And only the ones you're not allowed to eat. So if you don't have a bag, you can't store any food. No? This is more or less how it works. And so, but really, this process just goes forth and back. It's just like in a swing, you go forth and back, or in those things. How do you call those?
Seesaws.
Seesaws. You go up and down, no? But at the end of the day, you're again up or you're again down. So at the effluent, nothing really happens to the bacteria. The only thing is that these bacteria, after the nitrification tank, and keep that in mind, because this anaerobic tank we have at the very beginning. Because there, the wastewater, this anaerobic tank we have where there's a wastewater inflow. So let's draw that in a whiteboard, makes it more sensitive. This we have all treated. Oops. So again, we have our scheme 1. Blah, 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 blah. We have here our screen. We have a grit trap. We have our primary sedimentation. And now we comes here the recycling sludge, our bacteria. And now we have this tank. And at this point we have bacteria as a heterotrophic. We also have the nitrifiers. We have COD, no? And we have ammonia. Now, the nitrifiers sleep, no? Because this is only stirred, no oxygen. No, because we have here no. This is anaerobic. No oxygen, that means no oxygen. No DO, dissolved oxygen. No nitrate, no? So what can you do in heterotrophic? They can polyphosphate, go into phosphate, into autophosphate. This autophosphate they release into the wastewater. And they can do substrate, the good food, into PHB, polyhydroxy butyric acid. So they get the good food. Then we come next. Is our return sludge, no? And if you look at the scheme, then we have here our recirculation. And our recirculation has NO3 and it has bacteria, no? All of them, no? Because it's not selective, no? But no COD, no? But we have, here we have still, because only part of the COD is gone, here we have COD, and we have our bacteria, no? Oh, then I have to make green. So what happens now? This is now nitrifier sleep. And heterotrophs, what do they do? What did they do?
Or they would start using their PHB.
Hmm? No.
No?
No oxygen.
No
Well,
oxygen.
the important part is they might use it or not. What is important is they denitrify.
Yeah.
No? Because they have COD, there's bacteria, and there's nitrate. No? So this is denitrification. No? And of course, what we have is ammonia. No? No? But the nitrifiers can't do anything because they have ammonia, but they have no oxygen. Okay, here now we have our blower. And so this is our nitrification, because what comes out here is still COD, still bacteria, and still ammonia. But no nitrogen, no? No NO3. Because this comes out here. And you really can see that because you find foam on top of it and you might even get a little bit of bulking sludge if you don't stir it well. And that's due to the flotation effect of the denitrification. No? Okay, and what you do here now is, here you have nitrifiers. And you have heterotrophs. And this is here. Now everything is gone. Oh, and the heterotrophs is, of course, this is important because we're on the BOP process. Then, of course, they do PHB. It's also going to, because this is COD, and we have BO4 is going to polyphosphates. No, they build up again the polyphosphates, which you have here. No, because if they wouldn't have the polyphosphates, they cannot grab the substrate. This is something that goes together, and this has also to go together here. It's kind of now can discuss along which COD is helping them to build up the because those ones that find out that building this poly P, they just grow faster, and this is why they become dominant, because they grow faster. No? This is what we had, in between. Always those bacteria that grow faster, they become dominant. No? And the others that go slower get lost. And this is how you can train this process. This only was developed, was only recognized in the late 1980s, when BOP started. It's now become a standard method. There was all kinds of concepts to do that. There are more or less, there's also a large variety of process alternatives, how you can realize and optimize it. This is a little bit too short. I would need much more time to do that.
Just out of curiosity, my understanding is that polyphosphate and PHB form sort of a complex inside the vacuole. But for that to happen, there's some critical concentration of calcium ion. Do you know anything about that from a wastewater perspective?
No.
Making sure there's enough calcium.
I want to know that from you. This is where I need my microbiologist. Because this is now what I told you, for the recovery of phosphate, I need to tune that process.
Yeah.
And if there's anything critical, I need a microbiologist to tell me. That's something, if you have expertise, I even would invite you on my costs to Germany. If you can help us there. And we don't need the DAAD. Then I know a company that's paying for us.
Because I think there are a lot of like really interesting questions here. I mean, of course, you got the calcium, but like the other thing that kind of concerns me is, I think maybe this view that not touching the PHB under anaerobic conditions during denitrification might be overly simplistic. Because if you've got other electron acceptors in the system, like acetate under anaerobic conditions, that might give them enough, wiggle room to actually kind of start to chew up their PHB. Be kind of interested to do a carbon flux analysis and actually get a feeling for what's actually going on here. So, the net change might not be significant. There still might be something going on there.
Yeah, that's what they told me. The pilot plant is now really close to getting started, because so I have a biological pilot plant just like that, no? And now, of course, what my idea is to have here a pre-acidification, and then have a separation here to get the sludge out here, PS, and to get here flow enriched, no, with HAC, and then having put this in here, and having put this in here, and having part of this bypass this. And then from this effluent here, take part of it, put that in a separator. This depends, no? Take my surplus sludge out here, because that's low in phosphate. Taking the effluent, putting in manganese, and putting in the filtrate of digested sludge, digester. That means NH4. And then taking out here my MAP, no? As a stravit.
Yeah.
And then giving this stuff back here, and that's it, no? This is my bioprax process. And this is what I want to optimize, no? This is my baby, and there's a Calprax process which was developed by CNP US, and I work with CNP, and they want to optimize that as well, because our Calprax process still doesn't quite meet the standards of recovery which we have in Germany, so we have to optimize it a little bit. Then we have also a certain idea how we can do that. But really finding out what happens there and looking at the microbiology, and this would be very interesting, because you can look at probably, I can't look at the vasculars. I can't see him, and I can quantify him. And this, of course, I need someone to do that.
Mm-hmm. Yeah. I mean, one thing that, like, for instance, one thing I want Lisa to try, so she's been using this Nile red method to quantify, like, PHBs. But the old school way, from good old Slepsky paper from the 1950s. It's basically just acidified measured as a protonic acid equivalent. But when you're doing, these measurements in the UV part of the spectrum, there's a lot of other crap in a complex system like this that's going to interfere. So,
I don't need problems, I need solutions.
I know.
Okay, let me finish this
Yeah,
and then
sorry.
let's talk on that, huh? Because else your girlfriend has to cut out too much. Eh? Okay, under anaerobic conditions, the phosphate accumulating bacteria, BABs they're called, but they are normal heterotrophs, so they don't have anything to do with AOBs or NOBs, no? It's no, PAB is phosphate accumulating bacteria. No? Degrade in their cells under aerobic conditions accumulated polyphosphates. This degradation of the polyphosphates enables microorganisms under anaerobic conditions, because here, this is also something the students have to learn. This is anaerobic. This is what we call anoxic. And this is what we call aerobic or oxic. No? Because here you don't have this. Anaerobic is no DO, no chemical bound O2. That is no NO3 and SO4, no? And of course NO2. Anoxic is no DO, but NO3 or SO4. Basically it's NO3, you know. And aerobic is of course DO, no? And this but this end is not important, no? The basic conditions is this here. Just to understand the terms, no? This degradation of polyphosphates enables the microorganisms in an anaerobic condition to extract biodegradable compounds from the wastewater and accumulate these compounds in the form of polyhydroxybutyric acid in their cells. Degrading in the cells accumulated polyphosphates, the concentration of autophosphates in the water increases because it's put into the water. Figure 19 shows what happens here, and there's two pictures. This is what is from here. It's 0 to 4T. So you see in the anaerobic phase here, this is what happens in solution. In the solution, the phosphate concentration from the inflow, which is about 8, because it's 16. If you have 100 liters per person a day and 1.6 grams of phosphate, you have a concentration in the inflow water of 16. If you now mix it with 100 liters of inflow with 100 liters of return sludge, and the return sludge has close to 0 phosphates, you start with 8. So at the end of the day, if you're good, you end up with anywhere close to 30 at the end of your anaerobic phase, and I want to get to 60. And then in the aerobic, you get up and you go down to almost close to 0. Because in Germany, this depends how good your substrate is and how good your process is. There is plants that really do not have, it's anywhere between 0 and 5, no? So some have to precipitate in order to meet the effluent standard of small plants less than 2 and large plants less than 1. No, so I think it starts anywhere with, if you have more than 20,000 PE connected, you have to have a phosphate elimination, you have to meet the standard of 2. And if you are any more than 100,000, you have to meet the standard of 1 milligram per liter. Total phosphor, no? As measured as phosphor. And This is what happens inside the bacteria. The bacteria start with 90 to 100 milligrams P per liter in the sludge, and at the end you have 60, and in the aerobic zones you build it up again. No? And this is what is the low molecular weight polyphosphates. This is the high molecular weight polyphosphates, and this is the assimilated phosphor in form, also phosphate, which is in the DNA, ATP, ADP, RNA, and what else you have. No? This is what you basically have. This is what all bacteria have, and this is what you see here. Again, this is in conventional equipment without this training. Then you will find you have mostly this assimilated P, and then you have this high molecular polyphosphates, which are in, I think they are in the cell membrane mostly, no? The high molecular.
The high molecular polyphosphates, aren't those mostly contained in the vacuole with the PHB? Pretty sure.
Oh.
Yeah.
But it's anyways,
Yeah.
but those are in all. And then this low molecular polyphosphates, this is what you see in the vacuoles, no? And this is normally a rather low, and this you can, so the total phosphor concentration, you can, as if here they say you can triple them, I think mostly you can almost double them. Normally they're anywhere between 2 and 3% of the volatile suspended solids, and you can raise it up to 6%. No? And then, and the difference is that after in the anaerobic process, all these low molecular polyphosphates are given back into the wastewater. But how the phosphate elimination works, normally you always take the surplus sludge at the end of the nitrification. So here you take surplus sludge with 2% of the volatile suspended solids with phosphor, and here you have 3 times the phosphor. You extract 3 times the phosphate with the same amount of surplus sludge, because the concentration of the phosphate in the bacteria is 3 times as high. And that makes a difference. So normally the phosphate is about, we take, this was what I told you, this is this ratio of COD, no? If you remember this, we had COD to N to P, and that was 100 to 2.5 to 0.5. And by BOP, you can make this ratio in, this is conventional, and BOP, no? You have then the thing COD to N to P is equal to 100 to 2.5 to 1.5. And if you calculate that, this is here, this is always 80 grams. After primary sedimentation, this is 10. This is grams per PE and day. And this is, no, this is, sorry. This is now, this is 80. So this would be 80 and 2.5, 2%, this is 4, and 0.5 would be 0.4. No, this is 2, no, sorry. And here it's 80, it's 2, and it's 3 times as much, 1.2, and which would be in the surplus sludge, no? This you will extract with the surplus sludge. And now the inflow, as it said, B, no, of the biology, is COD, N and P, is 80 10, and 1.6. No? Now those 1.2 here, no, this really is a significant reduction. And this 1.2 is very conventional. You might even get it a little bit higher, and then you can meet the standards. This is what happens. And this what's left over, the 8, and that comes, and nitrogen comes back after the digester. You have a return from the digester of half of the nitrogen, which you eliminate here, and the nitrogen which is eliminated was a primary sludge. So you really end up with 9.5. So you haven't done much on the nitrogen elimination, but we can do that with nitrification and denitrification. Now, if this is in the surplus sludge, how much of the phosphate comes back after the digestion? Because the digester is anaerobic. So all the phosphate, which you will have in your surplus sludge, is going to be deliberated again in the digester. So when this came up, at that time I was still working with Rödiger, so I said, okay, this BioP, nice to do, but they're going to have a problem because all the phosphate is going to come back from the digester and the filtrate. So I'm going to sell them a precipitation plant for the filtrate. No? So I already planned those things. And I even had them advertised and everything, no? Because I wanted to be the first one. What came out? And then when they measured the filtrate, there was almost no phosphate. I expected phosphate in the filtrate of 1,000 to 2,000 milligrams per liter. And measured was anything between 20 and 80. So I said, shit, what's happening? So at that time, I asked a Professor Seifried. He said, Mr. Pfeiffer, this is very easy. There's so much calcium which is concentrated in the digested sludge. This is all precipitated in the digest. In the digest, it's right. It's not anymore in polyphosphate. You're going to find it in calcium phosphate. And this is one of the things that proved Lisa also in her bachelor thesis, no? Because we made a fractioning. This is what Lisa made. I don't know if you have ever seen her bachelor thesis. That's what she made. She made for me a fractioning of phosphor I think she did it mostly in activated as a surplus sludge and primary sludge, and Niels did that before in digested sludge. We do that by, we have an ICP now. My chemistry colleague has that. So we make a filtrate, then we have the dissolved, then we add acetic acid. Now we don't add any more acetic acid, now we add sodium acetate in order to, but we're still doing some research on that, in order to re-dissolve the polyphosphates. No, we leave the sludge and then do a filtration. Then we add mineral acid to point and put the pH to 4, because if you add acetic acid, you end up also with almost 4 to 5.
Yeah.
So you get the calcium, magnesium phosphates. This is what our calcium magnesium phosphate fraction is, and then we make a pH to 1. That recovers the iron and aluminum. No, we can also 2 is only iron, and 1 or 0.5 is also the aluminum. And then we make a king water. Is that king water also? What? No, obviously not. It's a mixture of nitric and hydrochloric acid.
Aqua Regia. Royal water. Royal water.
Yeah, royal water. Okay, right. Not king water, royal. Also royal water microwave, no?
Yeah.
But that's the hard stuff. There you get everything, no?
Yeah.
And the difference is then that was assimilated. No? This is how we fraction it. No? We believe that for engineers it's a pretty good approach. No? So we have an idea what we talk about. No?
Yeah. There's actually one of the questions I wrote down here is like, okay, so how do you actually measure polyphosphate versus, the lower molecular weight phosphates? That's one way to do it.
That's the only practical way. That's where our technology, and analytical knowledge ends. do what we expect in the process to be done. No? Because since we are process people, we just do what happens in the process and we figure out, and so we can make some predictions what happens in the process. No?
Yeah. And just out of curiosity, what about loss of phosphorus phosphine during these processes? Is it significant?
I don't even know what phosphine is.
Swamp gas.
Okay. Okay. No idea. I hope it doesn't. I trust microorganisms don't like that.
Yeah, some of them produce it. So I mean, at least,
Yeah.
I don't know what in these communities produces, at least in swamps and bogs. But I mean, yeah.
Yeah, but they're not sufficient. I don't think. At least in this process, it's only short-term anaerobic. So I think nothing happens there. There's no really anaerobic bacteria established there. And I haven't heard of any phosphine being measured or ever discovered in biogas or from digesters. And since you put it in the motors, it has been analyzed pretty much. No, we found out there was what I call it's siloxanes, no? Because they deposit in the motors.
Yeah.
And I think those phosphine would also give us some deposits in the motor finally. And I think there would have been discovered if there be any significant quantities.
I mean, and if your phosphorus balances are pretty good, I mean, there's no reason to think it's going somewhere else. So.
No.
Okay.
Okay, in the aerobic phase, the phosphorus concentration can raise up to 6%, what we have seen here, of the dry organic biomass. In the anaerobic phase, it can drop to 1.5, whereas without biological P elimination, the phosphorus concentration says about always 2% of the dry organic mass, organic mass, the volatile suspended salts. Due to this change of the phosphorus concentration in the cells of the microorganisms of the activated sludge, in the waste with the phosphorus concentration rises up to approximately 10 to 15 milligrams per liter ppFO in the inflow, to 25 to 40 in the effluent. This is what we've seen here. In the effluent of the BioP tank, sinks to 1 to 5, no? Which we see here. And the biological phosphorus elimination is due to the elevated phosphorus concentration in the surplus sludge being now 6%, because here, this is the sludge that we draw away, and this is the sludge, and there you compare the 2 to the 6%. In comparison to the phosphorus concentration 2% in surplus sludge without P elimination. Biological phosphate elimination has so far only been realized for wastewater treatment plant with suspended biomass. For process with Cecile biomass, reactor has to be operated like a trickling filter in the anaerobic phase and to be flooded into the anoxic and anaerobic phase. By flooding and flushing the fixed media reactor, also surplus sludge can be removed. Such a system has, to my knowledge, however, yet not been realized. No? Also, Ulrich Kostbauer is playing around with that idea, but we are at the very beginning. Okay, this is now the end of the chapter, biological treatment. We are at 1 o'clock. This is pretty close. I do have a small chapter for, but it's just 2 pages, and it's just basically, for basic design, I would like to do that quick, because it may take half an hour and then we are done with it. No? Then the basic design, the process scheme of the most feasible process alternative, and for us this is presented in figure 1, and you see it there, it's always the same. No? Screen, grid chamber, primary, and then the through flow biological activated sludge treatment with an anaerobic tank for biophosphorus removal, as an upstream denitrification, and nitrification and secondary settling. This is a standard solution. If you look in literature, you will find loads of other ones. No? But you have to have a basic design that the result needs to be a process scheme, what is a favorable option for you. An extended process scheme includes quantification of mass component and energy flows, which you now would have to add. I did it sometimes in adding figure, but I kind of always normalize those figures to 1 PE or to 100 liters or 1 cubic meter or whatever. In a real work, you would now give those figures of what you actually have, no? and all those hydraulic and organic and nutrient loads you would put there, and just all well calculate them like we calculate the specific ones. Okay, an extended process scheme includes quantification, mass component, energy flows, as well as characteristic dimensions and process parameters of the unit operations. Now, you would now calculate what is the volumetric and TSS flow of the or load of the surplus sludge, of the return sludge, and then you have all those volumetric and mass flows or component mass flows which you have. Then you also can calculate the oxygen demand from the oxygen demand and the transfer coefficients. You can calculate how much air you're going to supply into the aeration tank. Then you can design your aeration system. No? So first you start with all those flows only. In the first process in the domestic wastewater, treatment is a screen. First, the type of screen and the mesh size have to be selected. The screens have to be designed for the peak flow, 98 percentile of the inflow, if you have an existing plant. The capacity should be defined amply, because later expansion is difficult due to the defined channel width. You know, you can change about anything, but if you have to change construction, it gets really expensive. So you know, rather put baffles in your channels and put a smaller screen inside, and so you can take away the baffles later and make a bigger screen in there, or make the screen with smaller mesh size if you want to do that later, and then you have to take the baffles away, because if you make a smaller mesh size, you're going to need a wider channel. No? And we forgot that in Wismar, and that's a pain in the ass. That's why we can't go from 6 millimeters to 3 millimeters, which we would like to do, but our channels are not wide enough. We cannot do this for the next 25, 30 years. No? So we tear down this building, but this is, you know, nobody's going to do that. So do those channels wide and put in some baffles. No? The capacity should be defined amply, because layer expansion difficult to the defined channel width. You can do that with baffles. Sizing of the screen is product specific, because you know, flow rate depends on how the screen is designed hydraulically. State of art is to provide washing and pressing of the screen goods. We discussed that. Without washing and pressing, severe odor nuisance has to be expected. As screens are the most troubled process unit in wastewater, you can see this here. This is a screen. No? There you see them. And this is how many defects you will have annually per 100,000 inhabitants or something. I don't really know what it is. No? It's just equipment failure frequency for the different ones. And this is just defects. This is also repair. This is winter, this is maintenance, and this is others not known. So you see there's a lot of things, you have to repack, or some, you have a rubber boot somewhere in there and that gets stuck in your somewhere. So this is really a pain in the ass. That makes the most work. So the consequence of that is, because you have these problems, no? The state of art by washing, blah, blah, blah. A screen the most trouble unit in water, a robust and highly reliable screen should be selected. Trying to save money here shall retaliate soon and hard. No? A hard commissioning procedure should be part of the contract of purchase of the screen. No? And testing the screen, you have to test if the screen is able to clear large amounts of screen goods without problems under stormwater conditions. No? It means, you know, if it's not robust, if you have mechanic equipment, this mechanic equipment, if it gets delined, it's going to destroy itself. No, this is all this mechanic equipment is sensitive, and delining is the main problem. Okay, so this is what you have to do when you buy it. You can't really you have to leave the construction a little bit open. You can make the channel, you can say, I want baffles, I make it wider than you need it anyway, so anybody can offer it. You look for what you need, and then at the end, you just have to fix the baffles to whatever is a final decision, because you have to wait, you have to tender it, and so you can't really have a prognosis what's going to be the result of the tender. You can have a desire, but maybe someone else will win the tender, and then you have to fix it to whatever he is going to put in. No? But I wouldn't change a construction, civil construction anymore, put a reserve in it, just change the baffles. Okay, that's all to the screen. Aerated long channel grip trap is state-of-the-art for domestic wastewater. On the basis of empirical research, German design guidelines recommend to provide a hydraulic retention time of 20 minutes or 1,600 seconds, also for peak flow. Figure 20 shows why, because it shows the separation efficiency of aerated long channel grip traps over retention time for different particle size, and figure 21 shows recommended profiles for the grid traps. So here you see we want the 0.2, it's an old research here, but it's still true. We want the 95% for 0.2 mesh, so that's anywhere between here, you see here 700, the 1100 is really has reserve. So minimum we should have some 500 seconds, and you show what the how much percentage it is, and if you look at this here and you want 95% of that, you are up here with 500, no? And then 1200 is really has a significant reserve. You might make it a little bit smaller, but again, it's construction, and you don't want to ever in your life change construction. And if you have aerated, you don't really need, if you operate it with not full capacity, you don't have any disadvantage. What has been done, mostly aeration has been, is overdone. You don't need that much aeration. You really need, the old guidelines recommend 1 cubic meter of air per cubic meter an hour, but 0.3 is more than sufficient. So don't make your aerator for the grid channel too big. It's not a really big blower, but since it's very, it's not nothing. It's a toy in comparison to the blowers you need for the aeration tank. So it's not the big deal, but rather make it lower, because if you put in too much oxygen, you will start a biological process, and you will get rid of all your good good stuff you want for your nutrient removal. No? So don't put in. It corrodes bubbles, so it has no good oxygen transfer. You don't want to have oxygen transfer, but you want to have the corrosive bubbles for having the maximum pumping effect. No? And because this is a little bit standard, here you see it again. This is aerator. Here you have your aeration, and then this is where the fat is, because the fat is accumulating here, and with a little you just bump it in here, and there it can floatate, and then you skim it away from here, and here you grab your sand. And this is just where you get this information for. I don't know. I stole it from my company, so I think they stole it somewhere else. It's because it's so old. It was a long time before I was born, at least. No? So I'll give you some indication. Okay, then there's a little bit also for primary settling tanks, which are mostly built from rectangular tanks, much less frequent in round tanks. Water depth in primary is 2 to 3 meters. Length to width is 5 to 6 to 1. Inflow pipe with babbles should be 1 to 1.5 to 2 meters apart from each other. This in order to safeguard homogeneous flow distribution over the cross section. The sludge cone should be able to store the primary sludge of 1 day. The effluent should be withdrawn with a jagged weirs. No? So this jagged weir is, you have a rear and you have a jagged. And it's the regular jacks, they tell if you have not the full capacity flow, so it runs through the jags. And so it will, it will take off over all the, it will be an equal distribution of flow over the width of the tank. That's why you have those jagged weirs. They are much more important, of course, in the secondary clarifiers. You have to have those jagged weirs, because I saw this in Lemberg, Lviv, and in the Ukraine. They had no jagged weirs. And so you're not going to have, it's not possible. If you have wind, if wind effects, then all the water is just going to flow where the wind drives it. And then you're going to have, then you get a current, and the current is going to get the activated sludge, and you're going to have suspenser, really high suspenser, much more than 30 milligrams per liter you can have in the effluent. So these jagged weirs are very important. And of course, you have to provide that not too much sunshine and wind. So you should have a significant freeboard in second, and it's not so important in primary, but it's really important for secondary, because if you have a spot where the sun shines, all the sludge will come up there, because water density is less, and so it really get the density flow. No? And or if you have wind like in Lemberg, it's terrible. No? You can wreck about 30% of your treatment efficiency by suspender being in the effluent. No? So this really is important. No? So the effluent should be withdrawn with a jagged weir. The weir length should safeguard an overflow of not more than 180 cubic meters per hour and meter. In an effluent secondary, it should be 60, not more than 60. Okay, now with the given information, technical literature in form of the equipment suppliers, a draft design and rough calculation of materials required for the construction should be possible for the mechanical wastewater treatment. Any design should, however, be discussed with experienced consultants, M&E contractors, and wastewater operators. I still do that, so if you have not much experience, you're very well advised to do that. The more complex is the design of the biological treatment process, especially for the activated sludge treatment, with nutrient elimination because of interrelation of biological reactors and secondary clarifiers. The required information, however, is given above, and we made some specific design. And if you would be present here, I would be delighted to offer you the development of an Excel scheme to make a calculation for an example. That's what I do with my students in class, and they have to do that, of course, in the examination. But you're not here, and you're not willing to do an examination. So you have to do that now by your own. If you're interested, you can send me anything, and you'll get a response if it's done well or not. But else, I'll leave you to your professors to do that with you. And I thank you for your attendance and for your attention. And yeah, that is all I can do for you right now. And colorín colorado, este cuento se ha acabado. That's what it is, what they say in Spanish, no?
Oh, fantastic. Actually, I got a lot out of this.
That's good. That's what it was for.
Yeah. But, I don't know, I wonder how, have you ever seen like a small wastewater treatment system set up that's maybe the size of a bench top? Students can actually get their hands on and sort of play around just to see how materials move in the relative scales of the different vessels of the different stages of the system.
Yeah, they sell that, and you can buy it for 20,000 euros from Gund, but you can make it yourself.
Yeah.
And not have someone make it yourself with some peristaltic pumps and what you have. Yes, it works. It's also, you can also do that. You can build a continuous one. It's really easy. You can make it out of transparent plastic. No, it works. No, you will not have any problems really. You can buy a cylinder. The only thing is to find a cone. No, transparent cone which you can somehow fix to a cone where you can see it. That might be a little bit touchy.
Yeah, I got a company in Reykjavik that makes custom plexiglass,
Oh, okay.
so that shouldn't be a problem.
Okay. Because only the other ones are, you can make circular or rectangular tanks, whatever is easier for them. Circular tanks are normally less because you just cut a tube, 200-meter diameter, just cut off a piece, make it maybe 50 centimeters high. But for aeration, you use the stuff from aquarium.
Yep.
No?
That works.
And primaries well, you can also make rectangular settlers. That might be also simple. Because what you also could do, you could just take a pipe. If the cone makes a difference, you take a pipe, you cut it at an angle, and just put a plate below. No?
That works.
That works, and then you just drill a hole around on the side there, or pretty much the corner, and take the sludge from there. That would be probably the easiest way to do it. Because
It sounds like it would actually be a lot of fun to just play around with, you know,
sure.
and,
Where do you get the wastewater from?
well, that's the problem. So, one of these days, I'm hoping to actually talk to the municipality here in Aquaray and see if I can, take some out of the pipe that would normally go into the ocean. Just use that as, something to play with.
Oh, yeah. That's what we often do when you have somewhere a pump sump. You go somewhere, they probably also have somewhere where they might have the pump sump. No?
Yeah.
And if you're allowed, you put a pump into the pump sump, you pump it up into like a 200 liter, how do you say, 200 liter container, which you get industrial container, which you can close and so on, and you make an overflow. You pump it to the bottom, you put in the lid, you put one pipe, put to the bottom, and you have an overflow that flows back into the pump sump. And you just let it run 24 hours a day, or however, or when you come, you let it run for an hour, and then you take a sample, and then you have maybe that you can empty it again. No? That makes it pretty easy. No? Then you just go once a week there and get your stuff. No? Get yourself the 30-liter canisters, maybe 3 or 4, and that's good for 1 week easily. Put it somewhere in the fridge or cooling chamber if you have. If not, it's cold enough here. Nothing happens really if you're not more than 20 degrees. Then you can use that for making experiments. It's totally okay.
Yeah. We've also got a brewery here that they actually just pump their wastewater directly into the ocean without going through the municipal system, and which they're technically not allowed to do anymore, but that could be another good source of really rich, high COD wastewater.
Mm-hmm.
Yeah.
How big is the brewery?
Not big. I mean, I don't even know what their capacity is. I mean, it would, elsewhere in the world, it would barely be considered a microbrewery. They're small.
Okay.
But they make all the Viking beer here in Iceland.
Oh, okay, Viking.
Yeah.
I haven't found it here sold, however.
You haven't?
No.
Oh.
I know Viking was in Bonus had Viking. No? Bonus. Well, here I bought Gulf beer.
Sorry?
I bought light beer because I didn't want to. I haven't seen how do they call
Vinbuden, yeah.
Vinbuden. Yeah. I didn't sell those, so I just bought this light beer. There's 2.8 or whatever. Just
Yeah.
drink double the capacity, drink twice as much. Just same effect.
That's too much effort. I prefer more concentrated alcohols. Yeah, I can get you a couple cans of Viking. I plan on going to the liquor store before I pick you guys up, so I'll just pick you up a 6-pack.
Well, don't worry about that. I'm going to be home in a week. I could have gone myself. I even passed a few. What I drank, have you ever, I bought that because I'm drank it for years. That's really very special stuff is Carlsberg Elephant.
Never tried it.
That's a strong beer. That's something special. Tastes totally different. Tastes, it's compared from the strength. It's comparable to Guinness, no? But it's light beer. It's not dark beer. That's something special. I kind of liked it. I bought me a 6-pack when we ran up to the ferry. I knew when we were sailing we bought that beer loads of.
How, the elephant?
Elephant, it's called. Carlsberg Elephant.
Hmm.
It's like bock beer in Germany. That's what the monks drank when they had to feast. They drank this especially strong beer. They call it Bavaria, they call it strong beer, stark beer. No?
Yeah.
They have a time that is between Carnival and Easter. That is a traditional feast time. They weren't allowed to eat meat and all this kind of stuff, so they drank strong beer.
Interesting.
Yeah.
To be honest, though, I've never really been much of a beer drinker. I don't like the flavor for some reason. I don't know why, but
Do you want the files there finally?
I actually put two of them on the desktop. I think it's just those two, right?
Yeah. Did you take them today? Because
Yeah, I copied both just before we started.
no, for you. Huh?
Yeah.